I'm happy to welcome you back to Multi-GPU AI Train the Trainer workshop. And today, together with CASTIEL 2 project, EuroCC2, Cineca, and Barcelona Supercomputing Center, we are happy to have you on our fourth day of workshop. So today, as always, we are starting at 9:30 a.m. until 5:30 p.m. with some lunch break between 1 to until 2 p.m. But of course, as you know, we might have some coffee break and some of the sessions might finish earlier or later. Of course, if you feel that we should have some shorter break on top of other breaks, please feel free to let us know. I believe that all the trainers and from our side, we are very flexible, so we are welcoming your comments. Today, at the morning session, we will have Elena Parachiv from NCC Romania, and at the afternoon, we will have Geert Jan Bex from NCC Belgium. And thank you again, everyone, for being here today with us. And yes, we can slowly go back to Elena. But before we do, please use your Discord for your questions, comments. Speak up, use your microphone. I believe also Elena won't mind. If Elena wants to see some comments or questions, I'm happy to jump in and to help her out. Thank you, everyone. And Elena, the floor is yours.
Thank you very much. Hi, everyone. My name is Elena. I will just share my screen and make this full. I think everything is okay.
Perfect. Perfect.
Okay, so I'm a scientific researcher at the National Institute for Research and Development in Informatics, which is also a part of the Romanian National Competence Center in HPC here in Romania. So today, my presentation is on computer vision. I didn't want to just put the name of computer vision as the title, so I upgraded a little bit to be more fancy, let's say. And going a little bit through the contents for today, I want to present you a little bit about the key concepts and the applications of computer vision, as well as deep learning for computer vision, because this is what we will go through as applications for today. Some computer vision tasks that are being used and implemented worldwide, and also some applications of deep learning in computer vision. I prepared some videos that can show you a little bit of how computer vision is actually applied. Then we will dive into convolutional neural networks and we'll talk about some architectures and also the convolution and pooling layers, which are the basis of convolutional neural networks. And go a little bit to vision transformers, because these are a new type of architectures for computer vision right now, based on the classical transformer, and I thought that it would be useful to also share a little bit about it as well. Then towards the end, we will apply a use case on retinal disease detection using convolutional neural networks. I will also share with you some application of vision transformers for retinal disease detection. But unfortunately, I didn't manage to integrate it into Leonardo, but I will also share the notebook with you, just to be if you want to further apply. And at the end, some wrap up and discussions and other questions or discussions related to what I will talk about. I'm sure everyone heard about computer vision. Computer vision is a part of artificial intelligence domain, and it focuses on machines that interpret and understand visual information, similar to how we as humans use our brains and eyes. It involves mainly teaching computers to analyze, to capture the information and to analyze and understand the images that they are capturing. So in this picture, let's say it is how computer vision work. Computer vision, as I mentioned, works like the human eye and the brain. First, our eye captures the image, send the visual data to our brain, and then the brain processes the information and transforms it into meaningful interpretation. In a similar way, computer vision system does the same. It uses a camera that captures the image. The visual data is then processed by algorithms to recognize and identify the objects in the image. And It is very important that those algorithms are usually trained on similar data, so similar images, in order to understand the input and the objects in the image. However, before the system can recognize these images, it is very essential to be trained on a huge amount of data in order to understand and recognize the objects in the image. As a key concept in computer vision, there are two main domains that computer vision covers. It involves image processing that refers to techniques that manipulate and analyze digital images. Some tasks that are covered by image processing concept are image transformation, and we can talk a lot about geometric transformations, Fourier transformations, intensity transformations, and so on. In order to process the image, for the image to be enhanced, we also have tasks covering image enhancement, such as histogram equalization, contrast enhancement, image sharpening, and color correction. For image processing, we can also use noise reduction techniques, meaning median filtering, bilateral filtering, wavelet denoising, and so on. There are a lot of techniques that can improve the noise reduction in image processing. Another part of another concept that is very used in computer vision is feature extraction. And it mainly involves identifying different elements within an image. So to extract the features that are mainly used and that are somehow relevant, the most relevant features in the image. To do so, there are some techniques that are being applied, such as edge detection techniques, in which we have computer vision algorithms, edge detection techniques, Kenny edge detector, and so on. There are some other techniques that cover corner and interest point detection, and also algorithms that focus on feature descriptors. And there are a lot. You can check them. This is just a summary of the main key concepts. You can check them by yourself, because there are a lot of algorithms that are being used, and this domain is continuously evolving. So there are a lot of other interesting and maybe easy to use algorithms right now. Some popular libraries that are used in computer vision. Um, I I selected some of them here. One of the most important is OpenCV, which is mostly used for computer vision tasks like image processing, video capture, and real-time applications. And just to have a brief overview of the main functions that the OpenCV have. Um, I found a Medium post here. It doesn't matter that much, but I will also share with you all of the links that I will present. These are the nine most common functions from OpenCV that are being used. Of course, we have imread and imwrite in order to read the image or write an image after we process it. We also have CVT color that is used to convert an image from one color space to another. So maybe we want to go from an RGB to a grayscale or vice versa. So this is the most easy function to be used as there is a function that incorporates all of this process of the image. If we want to resize an image, we can use a resize function from OpenCV. There are other functions that focus on blurring the image. So if we want to process the image and add some blurring, we can use Gaussian blur or any other blur method that is integrated into this function. Kenny is used for edge detection. So this is very important when it comes to computer vision applications. ImShow and wait key. ImShow displays an image, and the wait key is much used for waiting some milliseconds for the image to be visualized. Threshold is another function that is quite being used very often. It creates binary images from grayscale images, and it is very used in deep learning for computer vision tasks. Find contours and draw contours, other two very important functions for detecting the contours or drawing the contours on the image. These are very useful because you don't say a lot to find the contours in an image manually. You can use this function and it will help you a lot. Video capture and video writer. If we come to process videos, OpenCV also has some functions that are focused on video processing. Okay, another important framework and library that is mainly used for computer vision is TensorFlow. I'm sure that you heard about it, also about PyTorch. But just to be sure, you can use the TensorFlow framework on their website, and also the documentation from TensorFlow is quite huge. So and it is very well structured. So in order to develop a CNN or on recurrent neural network and so on, there are a lot of documentation on their website, and you can see from the beginning how to develop a CNN, for example, using a sequential model and so on. So this is one of the main library that is quite used for computer vision applications. Also, PyTorch is another library and framework that is very used and has a lot of functions that can help you a lot in developing CNN or another neural network. So I invite you to walk a little bit through the documentation of these two frameworks because they have a lot of information and um, and depending on what framework you like most, this is the framework that you are using. In this lesson today, we will use mainly TensorFlow, but for example, for Vision Transformer, it is a library in PyTorch that is called Vit PyTorch. So for Vision Transformer is to better use PyTorch. Okay, and another library that uses a lot of image processing tools is scikit-learn. I will also share this with you. I'm sure that you can find it very easily. But just to be sure, this is the scikit-learn page. When you implement it in in Python, there is sklearn library. So it has a lot of functions for classification, for regression, for clustering, dimensionality reduction, model selection, pre-processing of images, and usually in deep learning, it is very used for pre-processing the data set for training. Okay. Now, for deep learning for computer vision, because we talked about computer vision and the key concepts and application for it. When we want to use computer vision for deep learning, we start usually by learning neural networks and then convolutional neural networks. I will go a little bit deeper about convolutional neural networks in just a few minutes, but just for you to understand the concepts maybe more deeper. Um, they are mainly designed for learning spatial hierarchies of features. So we use convolutional neural networks to understand the local features of images in the data set. And in the presentation, I also prepared some useful links that can be further revised by yourself separately because it gives a lot of they give a lot of details regarding, for example, convolutional layers. So if you want to go deeper to understand convolutional layers, you can pass through this documentation. Of course, these are very concise, uh, and you have to, if you want to learn a little bit more about, let's say, padding or activation functions that are being used, you have to search for them separately because these are just the basis of how convolutional layers are being processed. But there are a lot of other things that have to be understood for learning convolutional layers. But I will also go a little bit through them in just a few minutes. Okay. Another task that is usually um, encompassed into computer vision for deep learning are generative adversarial networks, which are the GANs, and they usually consist of two parts, the generator and the discriminator. They work against each other in order for the network to generate realistic images. And there are as well a lot of other types of guns, each designed for specific tasks and for improvement. For example, these generative adversarial networks, which are the basic part of this type of networks, uses the generator and the discriminator. So the generator is mainly used for creating new data based on some patterns that are learned from the real world data set that is put as input for the network. For example, in computer vision, this generator creates images from random noise that resemble real-world examples that are being processed as the initial data set. The discriminator is another part of this kind of networks that evaluate the data that is produced by the generator, and it compares the generated images with the real world examples, and it outputs fake or real. So this is how these two type of networks into the generative adversarial networks are working. Besides this type of networks, we also have deep convolutional generative adversarial networks, conditional, and so on. So again, there are a lot of other types of GANs that are usually addressed. But again, this depends very much on the task that is being applied. We also have variational autoencoders. There are another type of networks for deep learning for computer vision. In this case, there are some probabilistic version of autoencoders, and they force the model to learn a distribution over the latent space. These are somehow related to the generative adversarial networks, but rather than using a fixed point, there are autoencoders that are being used in the computer vision that cover more than a fixed point related networks. And we have autoencoders, variational autoencoders, denoising, and convolutional. So again, based on the task that is being applied, there are some autoencoders that can improve this task. Vision transformers are another type of networks that is being used for deep learning for computer vision. It was generated after the transformer of the natural language processing domain. So in this case, the vision transformer treat images as a sequence of patches and process them using self-attention mechanisms, which are the mechanisms that are integrated into the vision transformer, somehow comparable to the convolutions that are integrated into the CNNs. We have vision transformers, which are called VITs. There are also swing transformers and convolutional vision transformer. I also provided some links for all of them. Another type of vision transformer, let's say, towards a more hybrid one, because right now there are a lot of researches that also apply CNNs with VITs. So maybe you can apply it in the section on application for today. But just so you know, there are a lot of research going on that uses CNNs to understand the local features of the images, and then these local features are provided to the vision transformers to understand the features as at a global level. So this is one, let's say, research that is quite developing nowadays. Um, Again, another domain that has been very important in the last years, considering the GPT evolving, and then also the computer vision domain developing as well, is vision language models, which integrate visual and textual information in order to process the images and understand the natural language. So it somehow combines computer vision and natural language processing. These are mainly used when we have an image with a text. So it is very important to, of course, have a huge data set of images that also have the additional text in order to create a model that can understand the image and describe the images in natural language. Maybe you heard about Clip, which is from OpenAI. There are also some other vision language models that have evolved, such as Align or Bleep. I also put some references to them in case you want to visualize them and to maybe test them further. Now, when we talk about computer vision, there are some tasks that are involved, such as, first of all, image classification. Image classification is the most fundamental tasks in computer vision. The goal is mainly to assign a label to an image from a predefined set of categories. Of course, we have to have an initial data set that has the image and the label in order to further go with classifying the images and developing a good network for them. Applications that in which image classification is quite used are the medical diagnosis. In a lot of applications that there are CNNs that are mainly used to classify medical images such as X-rays or MRIs, and they are used to detect several diagnoses such as pneumonia, tumors, or other relevant conditions. I think in the medical diagnosis domain is very important to have a good data set with various images in order for the model to see different types of pneumonia, different types of tumors, and so on. Another application which is quite used is autonomous vehicles. And the image classification task is very used in self-driving cars, in which this helps in identifying road signs, in detecting pedestrians, in detecting other vehicles on the road. So very much used in classifying the object that the model is visualizing on the road. And in retail, there are some models that that use image classification in order to organize and categorize product images. This enhances search functionality and customer experience. It is quite used in the fashion domain. Another task is object detection, which goes beyond image classification because we are not only classifying images, but actually identifying the objects that are in the image, because there can be several objects in one image. The models that are being used for object detection are quite vast, but the most relevant one is faster RCNN or YOLO, which is you only look once model, which is quite used for object detection, or SSD, which comes from single shot multi-box detector. The applications that in which object detection is applied are surveillance. This is used in security systems in order to detect and track several people, vehicles, or suspicious activities. This, of course, have to be in real time. In healthcare, there are a lot of applications that uses object detection to identify and actually segment some abnormalities that appear in images. And in manufacturing, object detection is used to identify some abnormal defects in products or that are going on production lines. Image segmentation is another task which involves partitioning an image into segments in order to locate objects and boundaries very accurately. Semantic segmentation is used to assign a class label to each pixel, and instance segmentation distinguishes between different objects of the same class. Is used in medical imaging because when we segment an image, when we segment a medical image, we want to emphasize several anatomical structures or to emphasize some abnormalities. And we can further precise some diagnosis or go further with treatment planning. For autonomous driving, segmentation is used to understand the environment, understand the lanes, the road signs, the obstacles that can appear on the road. The image segmentation is quite in line with object detection for this type of applications. And also in the augmented reality domain, because we have a lot of virtual objects that have to be integrated for a real world scene. So image segmentation is quite enhances this quite enhances this domain. Facial recognition is another computer vision task and identifies and verifies individuals based on their facial features. In this case, particularly CNNs have been used because they are very good in identifying the local features, so very good at identifying several edges or contours that can improve the robustness of facial recognition models. And they are mostly applied in security and surveillance. They, of course, are integrated into smartphones and in social media to automatically tag individuals in photos. Here I put some images that are related to the applications of deep learning in computer vision for the medical domain. We can visualize in this image. I'm not sure if okay. This image is from a startup in Romania, which is called Rayscape, and they first started with identifying tuberculosis on CT images of the lungs. And then when COVID-19 happened and there were a lot of misinformation regarding this, they acquired a lot of images that pictured the lungs of patients that were affected by COVID, and they also integrated this into their system in order to see how COVID-19 affects the lungs and how it can involve. It is quite implemented into the Romanian healthcare system, not at a national level, but in private clinics. So a lot of private clinics in Romania are using this type of technology in order for the doctors to be more to have more access to what can happen in a CT scan of the lungs. This image depicts skin cancer. So again, for creating a model that can be very good with a 97% of accuracy for a malignant cancer, we have to have huge data set with the different kinds of images like this. So there are applications and there are a lot of researches that have been going on into the skin cancer domain to detect based on just a photograph if a certain spot on the skin can be malignant or not. Another research and one of the most important one is related to breast cancer. Um, this is from an MIT research in which AI has been used for detecting the parts of a breast cancer image of a mammography, sorry, to detect the breast cancer spot in a mammography. So this is again another specific area that in which computer vision is very involved for a medical application. Another area is related to ophthalmology, in which there were a lot of applications for detecting diabetic retinopathy, which is actually very relevant to diabetes, because patients that have diabetes might not be aware that they have diabetes. So maybe on an eye scan, they can detect that that they might have signs of diabetic retinopathy. So these are some images in which computer vision applications have been applied to detect several spots that can help the doctors in detecting further this disease. Here I put some videos that can show you the applications of deep learning that in computer vision that are right now available and have been very much used. So this one, just a second. This one is an AI algorithm that has been used at the Tokyo Olympic Games in 2021. It's quite interesting as they captured a lot of images and a lot of videos from different sports and detected some very important criteria and features that were very useful for the participants. Another application is um, um, is called that Lumen. I don't know if you heard about it. Is again another Romanian startup that that have investments right now from Microsoft and Nvidia, so they are very huge. And they have implemented the computer vision algorithm into their glasses for the blind people to understand the environment that they are working into. So this is how the algorithm is applied. It detects the object around the environment, and these glasses are somehow like like a dog that is mainly used for the blind people, and let the human that is wearing them know if there are some people in front of them or other obstacles. So it's a quite interesting application, and I think it's very much worth searching for them. Okay, I wanted to also picture some other applications that are right now um, implemented. For example, in a farm, there are some computer vision algorithms that are implemented into the cameras that are filming the animals in order to see if they are okay, if they are eating, and so on. I'm not sure where this application is implemented, but I know that there are huge applications in this agriculture domain that are very much evolving. This is a video from Waymo Robotaxi. If you know it, I think it's in the United States, and it is self-driving car that um, that is riding in the city, and it recognizes the obstacles and um, and it is very developed in terms of sensors and computer vision algorithms that are implemented in it. This is another application in the agriculture domain in which there is a camera that detects if the strawberry are if a certain strawberry is good to be taken. So this can take the job of some farmers, but it is very helpful for this type of companies. Okay. Before we go into convolutional neural networks, should we take a 5-minute break? It's okay?
Sure.
Yeah,
5 minutes. Yes.
Okay. It's okay, right? You can see.
Yes. Perfect.
So as I talked in the beginning, I will focus a little bit today on convolutional neural networks, and mostly on a use case that is related to medical application. Convolutional neural networks, as mentioned previously, follow somehow the core idea of a standard neural network. They have weights and biases and transform the inputs into outputs through a sequence of linear operations, which are called dot products. Um, what is special about this type of networks is that they can take raw pixel values as input and gradually build up more meaningful representations. And in the end, they come up with class scores. These examples that are here are somehow related to the use case that we'll be seeing in just a few minutes. So the class scores are related to the class labels that the data set has. A CNN defines a single differentiable mapping from input to output and is mainly trained end-to-end by minimizing a loss function. Um, in um, um, in general, that there are used softmax, cross entropy as loss functions, but you can test any algorithm with other loss functions if you want. Um, okay. Um, a standard neural network takes, well, if you know, takes an input as a single long vector and passes it to all the hidden layers that is having. Every neuron is connecting to every neuron in the next hidden layer, and so on. And we can get to the output layer after passing the input layer through a diverse number of hidden layers. But if we take a classic neural network and we put a data set that contains a lot of images, it is quite impractical. And I put here an example in which even if we have a small image that is 32 by 32 by 3, if we go with a standard neural network, we will have a number of 3072 weights per neuron, which is quite huge, especially if we talk about an image that is 200 by 200 or 1000 by 1000, if we talk about images, maybe medical images that are quite large. So a neural network, a standard neural network, would require a lot of weights per neuron. And this can of course lead to having huge models, huge trainable parameters models, and they can further go to overfitting. So that is why convolutional neural networks solve this issue by keeping the image structure and using 3D feature volumes. So instead of having full connectivity, CNNs go on to local regions of the previous layer and gradually transform the raw pixels into higher level features. In the end, it compresses the representation into a compact output, which is generally 1 by n class scores, depending on the class labels that we have in the data set. Okay, so this is a picture of what I explained. This is a regular 3-layer neural network. And here it is depicted how CNN is working by having this this three this this these features based on the 3D feature volumes that is integrated into CNN. Here we have a picture of how a convolutional neural network is working. So first we have an input which is represented by an image. Let's say that is 32 by 32 by 3. So in this input we have the raw pixel values with 3 color channels because we have that 3 at the end. So we have 3 color channels. First, we go through a convolutional layer that computes the output of neurons that are connected to local regions in the input. How this is done? By computing a dot product between the weights and a small region in the input image. And you can see this here. This is how convolutional layer is working. We have a kernel filter that is going through patch of the image and is composing this dot product. Going further through an output volume of 3 by 3 by 2, 3 by 3 by 1 first of all, and then if we want to also apply another filter is the output volume goes to a 3 by 3 by 2, and in this output we will have the most important features on that specific region of the image. So that is why this is more compressed than using the raw pixel values that we have in a standard neural network, because using filters that enhances several features in the image, we can have an output volume that is providing the most important features of that region of the image. Then we have an activation function that is applied generally after each convolutional layer. This is in most of the cases we are using rectified linear unit activation function, especially when we talk about images with various objects and so on. The pooling layer is the pooling layer appears after a set of convolutional layers in order to perform a downsampling operation along the spatial dimensions. So in order to maximize the features that are depicted after a set of convolutional and activational layers. And as an example, it's mostly used pooling layer is max pooling because it takes the maximum value of a certain region. It is usually applied with the 2 by 2, so a stride 2 feature for this. So if we have this slice that is that is resulted after the convolutional layers, we can take 2 by 2 filters in order to have the result of the maximum number, the maximum Oh yes, the maximum number of that region. Yes. So this is the pooling layer that, as we can see here, is it appears after a set of two convolutional layers. And in the end, we have a fully connected layer that is actually the layer that does the classification of an image. It results in the volume size of 1 by 1 by 10. This 10 is associated with this particular image as they used the Cipher 10 dataset, which has 10 categories, 10 classes in the end. So that is why this is the size of a fully connected layer. But in general, it's 1 by 1, and the n classes that we have for a specific dataset. So these are the convolution and the pooling layer, and some building blocks that are very relevant to CNNs, and we can modify in order to improve the accuracy and the loss function, the loss of a CNN are specified here. First, the kernel size of the convolutional layer. Usually a 3 by 3 kernel size looks at a very local structure. So we use 3 by 3 if we want to see small edges or tiny textures. We can also use larger filters. They are mainly used for seeing also the neighborhood of a certain region, but they really increase the computation of the CNN. The number of filters per layer is a very important building block because it specifies how many different patterns that the layer can learn. So if we increase the number of filters, the layer can learn more types of patterns in regions, but they can do it in parallel. So one filter might respond to edges, another filter may respond to specific textures of the images, and so on. The stride and the padding, they mainly control the spatial size of the feature maps. And a bigger stride is mostly used to downsample more aggressively. So the training becomes faster, but we really risk of losing small and fine details if we have a bigger stride. The padding is especially important if we have borders that shrink quickly. Um, and a padding size is very important and is usually used as a 2 because we mostly use max pooling layer. Yeah. Sorry, the padding is actually a 1 because if we go to this um, to this image, we can see that the padding is this level of zeros um, that are put on the edges of the regions in order for the filters to have a much broader view of several regions in the image. Okay.
Elena, sorry, there is one question in
Yeah.
Discord. Mm-hmm. You can check out.
Yes, just a second that I don't. Okay. Um. Okay, so as we have strident padding that are very much used in for convolutional part of the CNN. We also have the pooling, which is a maximum of or average, but max pooling is mostly used for CNNs. And finally, the depth, which are the number of layers or blocks that we integrate into the CNN. If we want a bigger number of layers, we can have as many number of layers as we want, but a deeper network leads to a more expressive but harder to train. So it might be easier to overfit. So we have to make sure that the number of layers that we integrate into the network is somehow balanced in order not to go to overfitting. Some other regularization blocks are also used. We have data augmentation, we have the dropout layer that is usually integrated at the end of the network. Weight decay or batch normalization, I think we can visualize them a little bit more when we go to the actual application. Um, Here I put some, mm, let's say the most popular, but I think that there are a lot of more, but let's say that these are the basic architectures that are being used for deep learning models in computer vision. AlexNet is one of the pioneering deep learning models. It has been launched in 2012. And it actually won the ImageNet, the large-scale visual recognition challenge. It involved this type of architecture. So as you see, it's a little bit simple, but at that time it was quite huge and computationally very expensive to implement this type of network. So we have a convolution, a max pooling, another convolution, another max pooling, three layers of convolution, one layer max pooling, and then two fully connected layers in the end with the softmax function to further classify the image. This is how this model looks like in TensorFlow, so using a sequential model. Um, I'm sure that maybe most of you are familiarized with computing CNNs, but for those of you who are not that used to this, these are some functions that are being used to add a convolutional layer, a max pooling layer, and a max pooling layer. And as you can see, there is the conv2d function, which is again associated with the TensorFlow framework. This used a kernel size of 3 by 3 for all of the layers with an input shape of 32 by 32, meaning that the images were from the ImageNet dataset. If you know the ImageNet dataset, there are small images representing certain things. So that is why the input shape is 32 by 32 by 3. And then they also add the activation function, which is relu, and then a max pooling layer for upgrading and enhance the features. We go with another convolutional and max pooling layer, then the three convolutional layers that were presented in the schema before. The max pooling layer, a flattened model is a flattened layer is used to convert um, the matrix that results after the last max pooling layer into a one dimension vector in order um, to be further go to the fully connected layers. And we add the dense layer in the end in order to classify the image. Another popular model is VGGNet. In this image, we have the VGG19 architecture. We have in this architecture, we have 19 weight layers. As we have 16 layers of convolutions and 3 fully connected layers in the end. Okay, this is one of the, again, most important deep learning architecture that was used and introduced in 2014. Again, for the same competition. And the components are mostly the same. We have convolutional layers, activation function that are integrated and are based on ReLU, pooling layers, and fully connected layers towards the end. Another model is ResNet, which comes from residual networks. It was introduced in 2015. Again, won the same competition for that year. It was developed to overcome some challenges that the very deep neural networks had, because these residual networks encompass some residual blocks that uses these skip connections. These skip connections are used to allow the model to learn residual mappings, because instead of going further as classical CNN is doing, going further and with direct transformations, and not keeping the previous layers into the flow. This type of neural networks have been launched in order to prevent vanishing gradient problems, which were very big problems when it came to CNNs. So these skip connections are used to let information flow directly across layers. ResNet is actually helping building networks with hundreds or even thousands of layers. So we are talking about a ResNet that has 152 layers, 200, and so on. So that is why it was very good to encompass a huge number of layers within, because of these skip layers blocks. These are some challenges that deep neural networks have before the launching of ResNet. Two major issues were being appeared at those times, and they also appear right now, but it's a problem of how the structure of the architecture is developing. We have vanishing or exploding gradient problem, and this is due to the number of layers that we have in a neural network, which if we increase the number of layers without managing them very thoroughly, the gradients of the loss function can become extremely small, and that is why we have excessively large weights during backpropagation, and also lead to overfitting the model. There were also degradation problems in which we talk about the performance plateau and accuracy degradation, which is correlated with how the model performs on unseen data. So these were the challenges that deep neural networks faced before residual networks have been launched. And together with the ResNet, another popular model that has been has improved a lot the field of computer vision and the field of deep learning for computer vision is DenseNet. And they addressed feature reuse, vanishing gradients, and parameter efficiency. And if we compare traditional CNN architecture in which every layer in the CNN is connected only to the subsequent layers, DenseNet wants to establish direct connections between all layers within a block. This type of connection enables each layer to see feature maps from all the preceding layers as inputs. It is very important because this is how we foster extensive information flow throughout the network. So each layer is somehow aware of the feature maps that the previous layers have produced. And this is how DenseNet appears. It uses as ResNet, as I was talking about ResNet, that it encompasses a huge number of layers. DenseNet was also produced to also have a quite good number of layers. We have DenseNet 121, 169, 201, and also 264. So as I was saying, the important aspect of this type of network is that each layer receives the output of each previous layers, and this design had led to major advantages such as improved feature propagation. We can go to a better gradient flow and also parameter efficiency. So we can have fewer parameters, and there are fewer parameters in the DenseNet, and can be compared as a performance to other architectures of similar depth. Okay. Now, one of let's say architecture that has been very much used in the last years is vision transformers. And here is a picture that this is the picture from the Vision Transformers paper. I modified it a little bit just to address the use case that we will apply today. What it does. So the vision transformers, as mentioned in the beginning, is a new method for image classification, and it encompasses self-attention mechanisms compared to the traditional convolutional filters that a CNN has. Um, a CNN uses convolutional layers to extract features and especially the local features um, of an image. Vision transformers divides an image into non-overlapping patches. It further goes to a module of linear projection of flattened patches. The OCT patches are then transformed through a are then transformed and gone to a transformer encoder. What this transformer encoder does? So um, each patch is embedded through this linear projection of flattened patches. So each patch embedding is passed through the transformer encoder, which consists, as you can see here, in more repeated blocks, let's say, because we can have multiple encoders that looks like this. So a multi-head self-attention allows each patch to attend to all others in order to model global context. Then we have a feed-forward machine multi-layer perceptron, which has a residual connection, and these residual connections are the skip connections that I was talking about at the ResNet. These stabilize training and preserve feature flow. So this is the transformer encoder that does a lot of normalization, again, multi-head self-attention, which is actually the core of the transformer encoder. Then we add the output from the multi-head attention to the embedded patches, normalize this output and go again through the multi-layer perceptron. We add with the input from this point, and so on. Considering the number of layers that we have in this that we propose to have in the vision transformer. After that, the result is going to the multi-layer perceptron head that is actually doing the classification of the image.
Sorry, Elena, for interrupting. We have two more questions on Discord from Jovan.
Yes, just a second. Okay, so another model that is somehow based on vision transformers is a deep vision transformer, which is again another function that PyTorch has. It is mentioned to be an improved version of vision transformer because it encompasses several new directions that transformer has. Especially DeepVid uses more transformer encoder layers than the original vision transformer. It uses a mechanism that is called reattention, which is like the self-attention for vision transformer, but at a much deeper level. And it combines hierarchical features learning with robust regularization strategies. What I want to also share about this is that DeepVid is a little bit more computing intensive, so it is quite huge to implement it. It can take some good hours if you don't have a good GPU. But both vision transformers and the deep vision transformer are very data hungry. So unless you have a data set that is very large to actually address these models, um, you might not have good results, and maybe they can also overfit. So they mostly depend on a huge data set for developing. Uh, okay, so right now, I'm switching to the use case that I prepared for today. I think we can have a 10 minutes break before this. Uh, Before diving into this notebook, I want to just have a brief overview of what the use case that we are talking about today is focusing on. So, um, what is the problem when it comes to retinal diseases diagnosis? The detection of retinal diseases based on OCT images has been an area of focus, mostly because of the prevalence and the severity of retinal diseases. We are talking about age-related macular degeneration, diabetic retinopathy, and so on. There are a lot of issues that can definitely cause vision impairment and blindness worldwide. So, just a small breaks, let's say. I'm not sure how many of you have interest into the medical domain, but if you have, and maybe we can chat afterwards. I finished the medical engineering faculty, and that is why the use cases that I proposed today is related to a medical issue. But I think that you would see maybe more clearly how this type of use case is used on a specific and a real world problem. So that is why I chose to include this. I hope it is interesting, and I hope that maybe the ones that you are not familiar with medical imaging or medical related domain would be a little bit more after this talk. Um, so, what do we need in this type of problem? An early detection for effective treatment and prevention of further damage of sight. Currently, there are in the ophthalmology departments from all around the world, the ophthalmologists usually manually interpret OCT images. And this can be time consuming. This can be also subjective because they can be subjective to the diagnosis of the image, and it can also lead to errors. So we want to automatically detect these diseases. How can we do this? With AI-based models and techniques that learn complex patterns and features. Of course, we have advantages and disadvantages when it comes to deep learning algorithms that are used in general in the medical field. For this particular case, it is the ability to detect the advantage is the ability to detect subtle changes that can be unseen by the doctors. They can lead to timely treatment and further prevention of damage. The disadvantage of this aspect is the lack of diverse and representative data sets, and of course, the interpretability of deep learning models. So the purpose is to, let's say, showcase a deep learning model based on CNNs. that can lead to early detection of retinal diseases. I talked about OCT. OCT comes from optical coherence tomography, which is actually a medical imaging method that provides a cross-sectional view of the retina. And based on this cross-sectional view, we can further see the distinctive layers of the retina. A retina is very thick structure. What it does is to convert the light that enters the eye into an electrical impulse that is further sent to the brain via the optic nerve. An OCT is a non-invasive, high-resolution imaging, and it enables us to visualize the anterior eye together with the morphological features of the retina. The measurements that are associated with this type of imaging are critical when we talk about retinal diseases diagnosis, such as choroidal neovascularization, diabetic macular edema, or the appearance of yellow deposits that are called drusen. And this is how an OCT looks like. This is from a normal OCT. I think the most important aspects that are drawn here is the retinal nerve fiber layer, because this layer is associated with the nerve fibers. Just a second to have the laser point. The retinal nerve fiber layer, which is this one here, is associated with the output of the cells that that is going further into the optic nerve. So its retinal nerve fiber layer is very important when it comes to diagnosis, and any subtle changes that are visualized on at this level can be critical for the diagnostic. So that is why this layer is very important. But of course, all of the layers are important, and all of the layers are altered when we talk about retinal diseases. So the data set that is also on the Discord, I will open it in a minute, is Kermani dataset. It is, I think, the most important dataset that is associated with retinal diseases, and one of the most important and the most big data set, because it contains almost 85,000 OCT images from almost 5,000 patients. This is the distribution of classes, so we can see that for choroidal neovascularization, so just a brief overview of how the images look like. These are one image from each class. So we have a healthy retina, we have a retina affected by drusen in B. We can see that this retinal pigment epithelium layer, which is this one here, is altered in drusen. The retina affected by choroidal neovascularization is in C. So we can see that the bottom of the retina is very altered due to the appearance of altered vessels in the retina. So that is why it's called neovascularization, because new vessels appear at the choroida level. And D, the retina affected by diabetic macular edema, as the name is suggesting, edema is associated with the accumulation of liquid at the macula level. So this type of retinal diseases can lead to more aggressive ones, such as age-related macular degeneration, in which we can talk, age-related macular degeneration is mostly associated with drusen and CNV. And diabetic macular edema is associated with diabetes and diabetic retinopathy. So this is one sample of image from this data set, and in this table is the distribution of the data set. Actually, we will see in just a few minutes on the notebook, because I also introduced the validation data subset of this data set. But just to have an overview, there are a lot of images that are associated with the CNV. So we can see that the classes are a little bit unbalanced. We will try to manage this issue by introducing data augmentation techniques. But we will see in just a few seconds. The diabetic macular edema is almost 12,000 images, and the drusen is around 8,000 images. So we have a lot of images associated with the CNV, which can be a little bit tricky when it comes to an AI model, because we have to be very careful in order not to um, be very to become very common with the CNV. So every other image that we can provide to it that was not seen by it, the model can misinterpret this image and associate this image with this class. Okay, so if we go to the notebook, the data set for the ones that maybe want to practice this later is at this path. I uploaded it just to make sure that everyone has access to it. I think that if you can download it also from the Kaggle website. As you can see, it has 85,000 images from 4 categories. It was published in 2018 within this paper. And it is also associated with another data set that also contains the X-rays of the patients that also went through the optical scans. So it's a quite vast data set, but what we are focusing right now is on the data set that is related to the OCT images. Okay, so if you want, and for the ones that don't have access to Leonardo, you can access this data set directly on Kaggle without actually downloading the data set. You just have to press here the code and create a notebook. It will automatically input the data set. So it won't be any problem with downloading and uploading again. So yes, for those of you that do not have access on Leonardo, this is one of I think the best way to do this, or on the Google Collaboratory. So either way is okay. The only disadvantage is that you have some accelerators here in the session options, but it lasts for some hours, let's say. So I think depending on the model that you are running, they provide you with a limited number of hours for the GPUs. But I think it's okay. I tested this data set on multiple models, so it was okay. Okay. So this is the data set, and it's quite large. It's around 6 GB. So it has a lot of images, but unfortunately, it's not that diverse. So we have imbalanced classes. Okay. Sorry for the appearance of the error, but yeah. I hope it will work in order for you to apply it and modify some things in the model to understand how it works. So as the libraries um, that are used and have been used for this notebook. We have the classical NumPy, pandas, matplotlib because we want to plot some graphics, Seaborn for the confusion matrix, and of course TensorFlow, as mentioned in the beginning of the presentation. I used TensorFlow for this use case. Because I'm mostly related and have been worked with TensorFlow, not that much on PyTorch, but they are both great libraries and frameworks for deep learning, and especially for computer vision. Okay. From TensorFlow, on the pre-processing part, I used image data generator. This will help me for the augmentation of the data because, as I mentioned, there are some problems regarding the number of images per each class. From sklearn, we import the metrics that we will use to evaluate the model and label binarize from the pre-processing function of the sklearn. So these are the categories. So choroidal neovascularization, diabetic macular edema, the appearance of drusen, and normal retina, which is associated with the healthy retina. So right now we want to see the number of images per each class, and we also want to plot. Right now, just want to see the distribution per training, validation, and testing. So we used this function that is called count images in directory in order to evaluate and go through all the train, validation, and test data sets. So we can see that for the training set, we have a number of 1,200 images. For diabetic macular edema, around 11,000 images. For drusen, 8,000, and for normal, another huge subset, 26,000 images. Now, as we previously saw in the presentation that we have for testing 250, I chose to separate them a little bit just to have a small subset of validation, because during training we also want to validate the images to see if the model is actually learning, and and that is why we also provide this validation data set to see to have the images with the known labels, but to actually testing it during the training in order to see the performance during training. So that is why I proposed for each class 8 images just to be sure that the model is training okay. Okay, and then for the testing data set, so for the subset that is focused only on the testing without seeing the labels, we have around 242 images per each class. So for each code block in this notebook, I also provided with some explanations, just for you to understand maybe a little bit more what are the problems or what are the explanations and how they are associated with this use case, especially in the healthcare part. Here I mentioned some things about class imbalance, and also why this is a problem because, for example, from the model's point of view, a CNN is trained to minimize error. So if we have a huge number of images per one class, in our example for CNV, the model will learn to prioritize this disease. So we don't want to do this, and we want to manage in a certain way this part, especially when it comes to healthcare, because we might have false negatives, which can be really dangerous when it comes to medical problems. And here I just put an example of how we can imagine this thing uh, in a normal and real world case scenarios when we train a medical student with 100 patients. 80 of them have this disease and only 5 have drusen. Of course, they will be more trained to recognize CNV, but they can be also trained that um, cannot um, cannot see the differences between CNV and any other disease. So how we can handle this part with data augmentation techniques. And image data generator is the most used function that is applied for data augmentation. And we can place in this function as many parameters as we want. If we want to rescale the image, to rotate it, to zoom it, to modify the width or height, to flip it, we can place here as many parameters as we want in order for the image to have multiple multiple modifications and alterations in order for the model to see each time another picture. Although it is the same picture, but it is quite different, just to be sure that we train the model for on a somehow diverse data set. It is not the best thing to do because ideally we want a better data set for especially for the medical domain. But this is what we can do in order to have a model that see um, multiple images on a certain task. Of course, there is the maybe you might wonder that if we want to use generative adversarial networks to generate synthetic images, it is one direction. It is very popular when it comes to augmenting a data set. But in the medical domain, it's somehow very sensitive because there can be very subtle changes in a medical image. So that is why these type of networks have to be very much aligned with with what a doctor might say and might approve or not. So yeah, but it is another way of thinking and another domain that is rising right now. Okay, another part that we can we can apply for augmenting the data set is the class weights, and these are different from the normal weights of the neural network. These class weights um, provide the model with some statements in order to pay more attention to the classes that are not so much represented. For example, just to have an example on this case, if we don't have that many images on Drusen, we can specify to the model that it has to pay more attention to this class by maximizing the class weight to a 2.5 value. This is somehow the value that is being used when we want to use class weights. So the underrepresented class is upgraded with or with paying more attention to, let's say, 2.5 weight.
May I ask a question, please? Yeah, so I was just
Forward, we want to explore the just one more thing related to the distribution of the training, validation, and testing. This is a code block that plots the distribution of them. So we can see that it is quite a big difference. For validation and testing is not a problem because they have the same number of images per class, but for the training is a very important aspect. Okay. Okay, this is just to see what the dimension of an image looks like, but um, the images from the data set are diverse in sizes. So one priority is to also resize them, just to make sure that the convolutional neural network will accept them, because the input of a CNN has to be the same size. So we put the image size to 128 by 128. So this is an example with a batch size of 8. What is a batch? When we train a model, we don't give all the data in one epoch, let's say, or in just in a direct training. We want to have smaller groups of images, and these small groups of images are called batches. So a batch is somehow like a small subset that the model processes before it updates its weights. In this explanation, I mentioned the batch size of 32 because when I tried to run it here, I had some issues, and that is why the batch size is on 8. But if you will try to run this notebook, you can switch to 38 to see if it works. For me, it didn't work, so that is why it's on 8. You can also switch to 16. Maybe it would be better in performance. But the initial, let's say, notebook had 32. That is why I explained it here for 32. And when we cover this batch size, instead of training a model on all the images that we have different batches with 32, or in this case 8 images per batch. So in the end, we will have, if we have 10,000 images at once, we will divide these 10,000 images by 32, so we will have almost 313 batches per epoch. So depending on the number of epochs that we have, each epoch will train on 313 batches with all the data that we have. Why use the batches? Because it is more memory efficient. We will have a faster training with this instead of working on all of the data. And here I explain what happens for each batch. So when the model does a forward pass, it uses its current weight to make predictions on the 32 or 8 images that we have in a certain batch. It computes the loss, and it does further a backpropagation. And through this backpropagation, we adjust the weights to reduce the error that we have in the previous forward pass. And then we move to the next batch and so on. This is somehow like just a short explanation of how we manage the forward and back propagation into a batch. Okay. Now we want to augment and apply rescaling for the training set. So that is why we used image data generator. For the training data set, we don't necessarily apply a lot of other modifications on the other types of data sets, such as validation or testing. We mostly want to apply it on the training set because this is the most interesting one for the model to, because this is the actual data set that it learns from. Okay. Here another I put it some explanation on why do we use image data generator. As I mentioned, it's a TensorFlow and Keras utility, and automates and simplifies the loading, rescaling, and augmentation of image data, especially during training. We want to rescale it from the RGB from 0 to 25, 255 to 0.1, because if we go to the raw pixel values, we of course have the range from 0 to 255. These are integer, represent color intensity, and feeding these values into a neural network of course lead to unstable gradients. It won't work and it won't give exact performance. And of course, neural networks are working a lot better when we have the ranges of values between 0 and 1, especially when it comes to activation functions, because ReLU is mostly working on the range of 0 from 1, from 0 to 1. Okay. In this part that is associated with the training generation, what we do is to rotate OCT scans slightly, to shift them sideways or to shift them vertically, zooming in or zooming out, flipping images horizontally, and so on. So it does a lot of alterations to the images in order for the model to see it differently. Okay. So this is used to read images from the directory. And then if we move to the model, because we arrange the data set, the images will be changed during the training. So it's okay because we applied this image data generation function. Now if we move to the model, to the CNN model, we can see that here we have 3 convolutional layers followed by max pooling layer. We then have a flatten function that what it does is to compress the output of the max pooling into a one dimension vector. Then we go to a dense function that actually does the classification, and then to the final dense function of TensorFlow that performs the final classification of the image. So I also mentioned this here step by step with the convolutional layers and what it aims, they are aiming to provide. The pooling layer that reduces the feature map size and speeds up a little bit the training and reduces the memory use and so on. We have the sequence of convolution max pooling, and another convolution max pooling. And a short explanation on what these blocks do is to, for block one, let's say, we provide the basic edges and the basic textures. For block two, we provide, based on these textures, the patterns of the textures, whether we are talking about curved vessels or other edges in the OCT image that is related and most relevant to the disease that is associated with that image. And block three, it computes abstract features, such as when we are talking about, let's say, an image on diabetic macular edema, maybe this block can provide a little bit more depth into the swelling shape. So the part of the image that is associated with the actual edema. Okay, the flatten layer, it converts the 3D feature maps that we have after the convolution and max pooling layer into a one dimension vector, as I mentioned. Then the layer that is doing the classification, it is a fully connected layer. This is what the fully connected layer is depicted in the TensorFlow with the dense function. What it does uses all the learned features to make the final decision. Why we have 128? It is again more general point of view of how to put this number of how to put an efficient number of units for this layer. So you can increase it, you can decrease it, but it might affect the performance in the classification. This is how this is a more general number that that it is being used. The dropout layer, because I mentioned it in the presentation, it's very much used at the end of the network to prevent the model from becoming too much dependent on specific features. And that is why this dropout drops and or ignores 50% of neurons during training. And somehow of an analogy with this is if we consider, let's say, a medical student that is being forced to diagnose without relying only on one clue, it trains them to be more general. So that is why a dropout is used, and it prevents overfitting, which and that is why it's very important to apply it at the end of the network. And the output layer with the function, with the activation function softmax, it's the final diagnosis. So it outputs it outputs 4 values, one of them being the most increased. So if we have CNV, DM, E, Drusen, and normal, and we have this output, this 0.75 being the most increased one is associated with the third class that we have in the vector. Okay, we propose the model, we want to compile it, and we use the function compile. I specified here the parameters that this function has, and we are talking about the optimizers. The most efficient one and the most used one is Adam, which is associated with the categorical cross entropy. And the optimizer decides how the model's internal parameters are updated during training. And these are some explanation of why this Adam optimizer was used. And as just a summary on it, it combines the advantages of stochastic gradient descent of momentum, which remembers past gradients in order to smooth out the updates, and the adaptive learning rate. Adam is very involved in the learning rate modification during the training. Categorical cross entropy is the loss that is again mostly used for the compile. What is a loss function? I think everyone already knows after these days. The loss function tells the model how wrong its predictions are. And why we use categorical cross entropy? Because we have classification on multi-class. We have a probability distribution. So categorical cross entropy is mostly used for multi-class classification. This is a summary. If we want to see the summary of the model, we can apply the model.summary function from TensorFlow. And here are some explanations regarding the model and the convolutional, the CNN as a broad overview. The model training is actually done with the fit function. It is associated with the model and we train it on the train generator. So the actual data set that also incorporates the image data generator, so the augmentation of the data which has to be during training. We also integrate validation data, so that 8 images that you saw before, these are validated. These are going through the training in order to see the validation accuracy and the validation loss of the model. And we perform this for 10 epochs. You can increase this, but it's quite, I think it's, let's say, okay like this, because it lasts for some time when it's training. So if we can see here, these are for epoch 1. This is the accuracy and loss on the training data set, and we can see that it is evolving and somehow leading to around the same value, so around 87, 88, which is actually okay, because we can definitely see that there is not that it won't overfit because it somehow stabilizes the accuracy. As well as for the loss, we can see that it downgrades from 80 to 51 to 41, and then towards to 0.34. So again, it somehow stabilizes the model. The loss of the model somehow stabilizes the values towards the end of the training. Validation accuracy and validation loss are the ones that are applied on the validation data set, as I mentioned before. So we train the model for this accuracy, and then we want to see how the model responds to data that has not been seen. So we can see that also the validation is increasing, and it is a little bit stabilized. Not it doesn't fluctuate very much. So I think this is a somehow good sign for the training of on this model. Now, after training, maybe we want to see how the model evolved. So the values that I described to you here for accuracy and loss can be plotted into a training and validation accuracy plot to see how they evolved in the 10 epochs, and for training and validation loss as well. After the training has been done, we want to evaluate this model on the testing dataset. Of course, as I mentioned, the testing dataset is the one in the end. The model has not access to the labels. It also access the images, and we compare the accuracy with the initial testing set. We have 94.63 images accuracy for testing subset, which is, let's say, okay. Of course, any model that passes 90%, 95% is good for a model that, especially in the medical related domain. We have to also look at the loss, which is 0.13. It is a little bit big, but I think that a problem was also the batch size of the model. So an increased batch size to 32 that was initially planned would be very good. And also the fact that the data set is quite imbalanced. Even if we manage it with data augmentation techniques, it is still not that what we want for a model to provide good performances. Okay, this is the classification report that resulted. So we can see here for each of the class, the precision, the recall, the F1 score for detecting each class based on the model. Okay, and the confusion matrix is the matrix that we usually apply towards the end of a CNN model to see how the model actually responded on the images from the testing subset. So we can see that, for example, the most misclassified ones were for the drusen. Of course, we can think about this because it is a quite small subset. So as I mentioned in the beginning, they can be associated very much with the choroidal neurovascularization. because again, drusen is a small subset in the image. Another misclassification that this model had was on misdiagnosing diabetic macular edema. So 12 images from the testing subset were misdiagnosed with the CNV. Okay, if we want to plot the receiver operating characteristics curve, which can have a view, let's say, which can provide us with a view of true positive and false positive rates per each class, we can use we used this function, and it receives as parameters the test labels and the test predictions. So what were the labels, the true labels, and what predictions have been done. So this is a good plot, let's say, if we are talking about multi-class classification, and it is quite used when we want to evaluate more than just accuracy, because we don't we cannot fully rely on only the accuracy and loss. We want to see how it actually develop, how it actually performed on if we compare the true labels and the predicted ones. Okay, so this is these are some explanations on the ROC curve. And towards the end, I also plotted some pictures from the data set, from the testing data set, to see where the model actually predicted the good labels. Just a second. So here are some of the images that were generated and randomly visualized here, randomly plotted. Most of them are CNV, and the predicted ones were CNV because, as you might figure, the one class that was predicted very accurate is CNV, choroidal neovascularization. But if we want to see some other images that are associated with other retinal diseases, I also put a function here that show us what some of the images that were on one label, and the prediction of the model was different. So that is why you will see in this output different use cases. Let's say the actual CNV and the predicted one is diabetic macular edema. We can see that it would be easier for a person like us as well to misclassify this, because we see these parts that are somehow associated with an edema at the macular level, but they were actually choroidal neovascularization. This in this image as well. Here it also misclassified these parts of the image as diabetic macular edema, which was in fact choroidal neovascularizations, because we see these parts of the image, and so on. So these are some images that I wanted to show you, and this is the model that I wanted to for you to understand. Right now, I'm not sure if Leonardo is working, but if it's not, you can You can try to test it on Kaggle maybe. And maybe what I wanted for you to test, or if you have any other ideas, I'm open to it. You can sorry, you can modify the model of the CNN, so you can add any more convolutional layers or max pooling layers that you want in order to see how the model is performing from three convolutional layers based CNN to maybe a bigger one. Or maybe you want to test some architectures that I presented, or maybe one DenseNet or ResNet. I recommend DenseNet because I also tested it separately, and I got good results on DenseNet 169, I think. So right now, the time that we left is for you to try to test it. If you have any other questions, I'm open to them. And yeah, I think that would be my presentation for today.
Okay. And let's minimize some stuff here. Okay. So let's skip this one. Let's skip that one. So basically, there are a number of conventions which I use in these slides just to emphasize things or to try and make things a little bit more clear. So, for instance, inline code fragments and file names and such are always rendered in this monospaced font in running text, so to make them stand out a little bit and make it easier to read these slides. Long code fragments, same font, but in a field with a grayish color. And for data files, don't remember whether there are any in this particular presentation, but different background color, so just to distinguish it from code. Sometimes you will see these ellipses, which basically means not enough screen real estate in order to show you the whole thing. But that means either it's been explained on the previous slide, it will be explained on the next slide, or it's pretty obvious, as in case of the data example, yeah, just more or the same, so nothing much interesting happening there. Okay, and then shell commands are rendered on a black background, and there is the $sign in front of it in order just to emphasize that it's a shell prompt. A number of icons, good practice, bad practice, potential hazards, potential performance issues, warnings, and so on. Okay, so these are the more practical things about this particular slide deck. Always useful to talk a little bit about it. Let's start with a bit of motivation. So basically, I don't need to tell you that machine learning is increasingly important, not only in and by itself, but in many scientific domains. It has been for quite a while very prominent in bioinformatics and in the medical sciences, but now, of course, also in chemistry, in engineering, and so on. So basically, it is getting pretty pervasive as what I would call a tool in mainstream research. It is always challenging to reproduce machine learning projects because there are many opportunities to get into trouble. And of course, that is a bit of a problem since at the end of the day, all of this is about science. If you cannot reproduce science, what are you doing? Collecting butterflies or something, but maybe not doing real science. So we have to take care of that. Is it always entirely possible to reproduce everything? No, but at least we need to try. And also, something that you see is that, okay, especially in bioinformatics, you have pipeline systems. which allow you to easily reproduce workflows. And that's a very good thing. But the problem is that the overhead to create a workflow is sometimes a bit of a limitation with respect to the flexibility you want in order to do experiments. So basically, there is a sort of a trade-off there. And all of this is the motivation for machine learning operations. And in fact, this is more like experiment operations, I'd say, rather than machine learning as such. Machine learning is just, let's say, the trigger in order to formalize things and create tools in order to support experiments. But of course, you can apply the exact same tools, the exact same ideas to whatever experiment, computational experiment you are doing in any domain at the end of the day. So basically, XOps might be a better name, but given that we have to get people to our trainings, if you call it MLOps, they're flocking. If you call it XOps, they just wonder what the heck you're talking about. So yeah, that's marketing for you. Okay, so if we look at the space of software which is out there in order to do MLOps, so products which are explicitly created for that purpose, there are quite a number of options. There is, for instance, MLflow, there is ZenML, and there is also DVC. And DVC is the one I will be talking about, and I'll also explain you why that is, what my motivation is to talk about this particular approach. So basically, DVC is, in a sense, older than MLOps, in the sense that the term wasn't coined at the moment when DVC was actually started to be developed. It's data version control. So essentially, you are all familiar with Git. That is a version control system typically for code, for text, for these kind of how shall I put it, artifacts. Let's name it like that. But you are familiar with Git, and you know that, of course, that poses restrictions in the sense that, for instance, on GitHub, you can't upload arbitrarily large blobs into a version control system. There are limitations. Another limitation, of course, is that differences on data sets need not necessarily be that meaningful in the Git sense of differences. Because, of course, data is not only textual, which is easy, but it can also be binary, which is a showstopper for a Git diff, because it doesn't know how to handle binary files. And that is actually where DVC comes in, data version control comes in, because DVC aims to alleviate these particular problems. So, in my opinion, DVC has a number of advantages. One of them that it interoperates with Git. Okay, is that an advantage? Maybe yes, maybe no. In my opinion, it is, because basically that means if you're familiar with Git, DVC is very similar, so that reduces the learning curve a little bit. Also, the way of working, how shall I put it, the concepts behind DVC are, of course, borrowed from or inspired by Git. So it's very Git-like, which is a positive thing. And another nice feature is that if you combine Git and DVC, you have something that works standalone, which is a good thing because, for instance, other MLOps frameworks typically require daemons running somewhere, servers running somewhere in order to do the things that you can do standalone with Git and DVC. And of course, that is an advantage in the context of HPC systems, because typically running servers alongside your jobs is possible, but it's brittle. And not all HPC systems have infrastructure in order to run servers alongside HPC jobs. So that's for me a good motivation to look at Git and DVC because then I don't depend on anyone, I don't depend on infrastructure, which is always a nice thing. DVC also supports remote data storage, and we'll talk about that in a bit more detail later on. But basically, it means you're not restricted to storing data on the system you're working on. It can be elsewhere, which is of course nice because that means that you can easily share it between projects, between project members. It has quite a number of features which are interesting. So the trivial one, in a sense, which is already quite valuable, is data versioning. Another one, which is also quite useful, is data pipelines. Again, there are many ways to encode your workflows into pipelines. Those of you familiar with bioinformatics might know SnakeMake or Nextflow or similar systems. So the data pipelines in DVC are, in a way, comparable to those. And then there is also, and now things get really interesting, experiment management. And we'll see what that means later on. There is also a model registry, but that requires DVC Studio, and that is not only payware, but rather expensiveware. So, okay, it does exist. I've never used it because, yeah, it requires a bit of an investment, literally in terms of money, and I'm not going there. Just mentioning it, if you're really into this, then it might be worth checking out. Okay, so how do we start working with DVC? Okay, let's deviate a little bit from the slides, and let me go to here for a second and show you a file. Where's my mouse? Oh, here's my mouse. Okay. So basically, I'm on. Yeah, that's annoying. Can I get? Yeah, I'll do it differently because I would like to see the first line of my terminal. So, okay, and preferably also the last line. Okay, that should fit. Okay. So basically, I'm on Leonardo right now in my home directory, and this is just the repository which you are familiar with. I'm going to the MLflow directory and into the tools directory. And as usual, in the tools directory, there is some information about stuff which is required for a particular training. So in this case, it is simply a README file, and that is not particularly interesting. Basically, the interesting part is, I thought it was the README file, but apparently it isn't. So basically, the one I want to show you is how to install DVC on HPC systems. It depends a little bit from system to system. I had to fiddle a little bit on Leonardo. I don't quite know how they did it. It's a good idea, but okay. So basically, of course, it can be installed using pip, and that's easy. But what is not easy is that on Leonardo, a pip install -- user doesn't work, which is good because that's the ideal way to shoot yourself in the foot. So it's a neat trick that it doesn't work, but yeah, that means you have to find a little bit a way around that. So for certain tools like DVC, like other, let's say Python-related tools such as Ruff and so on, which you can install using pip, I like to use pipx because basically it allows you to create an installation that is standalone. So regardless of your packages which are installed, everything which is required for a certain application is installed in your home directory, somewhere in the .local directory, and will run in isolation. So that's rather neat, because that means that you can run tools. Okay, of course, you could say, well, okay, why bother? What's the point? Well, basically, there is an alternative. If you have a project that involves Python, you can simply install DVC as part of the requirements for that particular project. And of course, that also works. But of course, as you can guess, that means that for each and every project in which you want to use DVC, you have to remember to add it to the list of requirements. You have to install it time and time again. I'm lazy. I prefer not to do that. I prefer that it is installed at, say, system level. And for this, pipx is a good approach. So basically, if you want to install it, then you can do so by loading a Python module. You not necessarily need to do that because Python is part of the system images, but remember that's a pretty old version of Python. So the Python that comes with the system on Leonardo and frankly on most HPC systems I'm familiar with is Python 3.6. It works. The problem is only that it will give you a very, very old version of DVC. So don't do that. Make sure you have a recent version of Python in order to install DVC. Then you get the latest version, not one that is 5 years behind. Okay, so modulo Python, very easy. If you can get away with installing pipx using pip install, great. On Leonardo, for some reason, that doesn't work. So basically, what you can do is just create a very small environment that is only intended to install pipx into it. Okay. And you create that environment, you activate it as usual, and then you can simply install in that environment pipx using pip, basically. Okay. Once you've installed it, you need to take a second step, and that is running using the pipx module, the ensure path command. That basically ensures that stuff are running in isolation. Okay, once you have installed pipx, you can simply install DVC, and it comes with a number of flavors, let's say. So basically, the easiest thing to do is just pipx install DVC all. Okay, that will install quite a number of connectors for a large number of storage backends. Typically, I don't care. For this training, I only need the SSH one. I don't need Amazon, AWS, etc., etc. So just to keep things lean and clean, I just specify the SSH extension to DVC. Okay. And then basically you can, after using pipx in order to install DVC, you can just deactivate the environment. You can unload the Python module and DVC is going to work. So that's quite easy. And then of course that will run independently from any modules or any environments you load using either virtual environments or Conda, Mamba, whatever you are using. There is one catch, which is important as a troubleshooting thing here. So basically you have to be a little bit careful, because if your Python path gets set somehow by loading a module or whatever, then things may go wrong with DVC. So in order to ensure that it really, really runs in isolation, you can simply define an alias with Python path is equal to nothing, so unsetting it essentially, and then DVC. So basically that would work quite well. So here's the example with the alias. So this would unset, in this particular case, the DVC would run in a sub-process for which the environment unsets Python path. So this ensures that DVC runs quite cleanly in any circumstance. Okay, so basically I've got pipx installed. Not, and that is weird. No, not DVC, sorry. pipx, yes, I have it installed, but then I need to load the module. And basically, if you have a recent version of Python, you should get this version of DVC, which is 3.66.1. Okay, so that's my very recent version. Okay, I'm going back to my home directory, top level, and I'm going to create a GitHub repository. So I create a directory. Here, right? And of course, git init. Okay. All right. I think that my branch name now is master. Okay, I'm not going to worry about that. So basically, I don't care that much. Okay, so I've got my repository. Now I need to initialize it for DVC. So that's the next step. And that's very similar, just DVC init. Okay. There we go. So basically, some commercial stuff and where to find documentation and so on, which of course is quite useful. I don't mind anonymous aggregation of usage analytics. If you do mind, there is a way to opt out. It's documented in the documentation. I never bothered to look it up. Given that it's anonymous and given that I'm not involved in any state secrets or defense projects, I don't really care. Okay, now this is a Git repository, so let's check Git status, and then you see that a number of new files have been created. You see a .dvc directory, and you see .gitignore config directory, or config file rather, and a dvc ignore file. Okay, so basically what I want to do now is to actually commit everything. As you see, it's already been staged for the next commit, so that's done automatically by DVC. So what I need to do is to commit this. Okay. All right. So basically that's it. Now I'm sort of ready, but not quite, because I will have to define some remotes to store my data. Okay, we will talk a bit more in detail about remotes later on. So basically, what I'm going to do now is something that essentially is a bit silly. What I'm going to do is just to create local storage, and that is going to be my directory where data is stored. So yeah, this is of course not really a remote. So this is just for demonstration purposes. We'll see what you can do alternatively later on. So that's DVC remote, and then add -b. What did I call that? Local storage, and the directory where I want that to go. So basically, let's call that very inventively my data. Okay. All right, so a remote has been added. Great. And it's also the default remote. okay, given that you see that there's a default remote, that means that it's possible to have multiple remotes. So the default remote is where stuff happens when you don't specify anything else. You can pick a particular remote if you like. You can add as many as you want to a project or to a project. That is up to you. Okay, so that is done. Great. And then again, let's have a look at the status of the repository. And as you can see, the config file of DVC has been modified. So this has not been staged. I have to stage it first, or I can just do commit -a -n. Okay, and reload. Okay. No, I did something stupid. What's this? Okay. Yeah, I should actually have because it's of course done on most of my systems. But anyway, it doesn't matter. It did some default things. Yeah, funny. It actually got my name from okay, excellent. Yeah, I can live with that as long as I don't do anything on GitHub. It doesn't really matter. Okay, so now we've got a remote. So let's talk a little bit about these remote storage options. The data itself is not going to be in your GitHub repository. It's not going to be stored in the Git repository nor on GitHub because it's too large. Okay, and as I already mentioned, it's also a bit of a bad match with Git because, of course, Git deals with text files, but it can deal with binary files, but not in an intelligent way. So essentially, you lose quite a lot of features which Git offered if you work with text files. You don't have them for binary files. That's one thing. Another thing is, of course, Git is about storing differences, deltas, and of course, a delta of a binary file is something interesting. Okay, so basically, DVC is going to store metadata in the Git repository. That's the idea. And the data is going to be in remote storage. That's the philosophy. So anything meta information is in your Git repository. The actual data is in the remote. For the remote, you have quite a number of options. You've seen the one I used right now, which is just a local directory. This is a bit boring, but for demonstration purposes, of course, it is quite enough. Then the second one is more interesting in the context of HPC, and that's of course SSH and or secure FTP. So basically, those are possible as well. You can simply define a remote that uses one of these protocols. It also supports WebDAV. It has a lot of support for all kind of cloud storage, Azure Blob Storage, Google, what is it? Google something something, Google Drive, Google Cloud. I don't remember what the P is for, platform probably, I don't know. But interestingly, it also just supports S3. So basically, if you have an S3 endpoint somewhere available, which you have access to, then of course that can be used as well. Okay. So basically, a few examples here. Suppose I have a remote in this case. Yeah, that would be for our systems. So let's not go there. And this actually I already showed you. Basically here things are a bit more interesting. So this is an example with an SSH protocol. So basically the remote is going to be in this particular directory. By the way, the user doesn't exist, so don't bother. In this particular directory. And that means that if I were to store data well, you already guessed that will be called pushing the data to the remote. That would mean that it would be transferred, in this case by SSH to that particular system. And in this case, it would use secure FTP rather than SSH. So as I mentioned, there is a lot of possibilities. There are a lot of possibilities to add cloud storage. Basically check the documentation because it's a pretty long list, and I don't have any cloud storage somewhere compatible with this, so I never tried. But basically it's just a matter of specifying your remote. Okay, so that was the preparation. Now we have a DVC repository or a Git repository with DVC support configured, and we can actually start using that. So basically, of course, we need some data. Okay, I do have some data in the repository, so let me copy that. R. That would be CASTIEL, front-end flow, data, no, source data, EC data, input. I'll have to check. Data pipelines, no. Experiment management. Okay, data pipelines will do, I think. Do I have a data directory there? Yes. Okay, so let's copy that so that I actually have some data. Okay, so the data directory is very impressive. It contains a CSV file, a single CSV file. Okay, fine. We don't mind that much. Basically, let's see what it does. So the first thing, and of course you recognize this from Git, the first thing you do is you add the data file. So dvc add data CSV. Okay, so basically, as you can see, this took a while because, of course, that file has now been cached. Okay, now, of course, let's have a look at Git status. Actually, DVC is telling me what to do, but let's just have a look at the status to see what is actually happening. You see that indeed there are a number of things. So basically, the data directory is not under version control, but of course, what I should do is I should add these directories, these files here. So let's have a look in the data directory, because now, as you can see, there is a new file. We had data.csv, now we have data.csv.dvc. Let's have a look at it, see what it contains. And as you can see, it is essentially an MD5 checksum of our data file. It lists the size, the protocol or the algorithm used to compute the hash, which is MD5, and then also path information. So this is essentially the metadata of our system. Okay, then as you can see here, let's have a look. If we do -a of data, then you see indeed there is also a third file, which is .gitignore. We'll also check that one out. And then you see that the actual data file has been added to the gitignore file. So basically, the only thing that Git is going to keep track of is the metadata generated by DVC, not the actual data. Okay, so git add data DVC and data gitignore. Okay. Git status, as you can see, everything clean, and I can do a git commit. Okay. Okay, let me, because this is getting annoying. Yeah, I can live with that. Okay. Whatever. Okay. Then at least I don't get these stupid warnings, I hope. Okay, so basically I added, I committed, and so on and so on. All right, so now basically DVC is aware of this data set and is going to track it. Very similar to adding something to a Git repository, and then it gets added as well. But note that we work with DVC on the one hand and Git on the other hand in tandem. So basically the only thing that DVC is going to do from Git perspective is generate metadata files or modify metadata files. Of course, DVC is doing more in the sense that it also actually keeps track of the data and will allow us to handle the data. Okay, so data can be essentially anything you want. It can be textual, so CSV files, JSON, whatever you like. It can also be anything binary, HDF5 files, images, Hugging Face datasets, whatever. Also, of course, tensor files of PyTorch or anything. I mean, it's not data, it's your model, but at the end of the day, it is data. Okay, what you can do is automatically auto stage, and that's a matter of configuring DVC. Then it will do that staging, which I did manually, git add data.csv, etc., etc. I added that to, this is actually, I forgot the .git ignore here, so I would have to update the slide, but okay, never mind. So basically, that's why it's always a good idea to actually have things done automatically. And you can configure DVC easily using DVC config. Again, sounds familiar. Yeah, that's exactly how you configure Git as well, but now for DVC. And then auto stage, core auto stage should be set to true. So DVC, config, core auto stage, and we set that to true. I write this. Okay. All right, so let's again see what's changed by doing git status. And then you see that indeed the thing which was changed is indeed the configuration file. So git commit dash a auto commit. Okay. And that is, of course, exactly what happens here. Except that I had a different commit message and that I didn't bother to stage it. I just used the -a for commit. Okay. So basically now, how do you interact with the remote? Because at this point, we have defined the remote, okay, albeit it's a very boring one, but how do we interact with it? Because the only thing that DVC has done up to now is compute a checksum for our data file and cache it. So essentially, it's not in the remote yet. So how do you get it in the remote? Simple, DVC push. Very similar to what you would do with Git. Okay. So now basically the file has been pushed. Okay, so essentially we can have a look what happened in our data directory. And indeed you see that there is something in there. there's the directory files, and there is a directory MD5. And essentially, there is this particular file. We can have a look at it, what it is. And of course, in this particular case, it's quite simple. It's just our original CSV file. Of course, if this were a binary file, then we couldn't look at it this way. And it might also be sharded. So basically cut up into different chunks and stored in a variety of directories. For our simple example, that's of course not the case. Okay, just like you push data to a remote, you can pull changes to data from a remote just by using DVC pull. That's the exact same thing. One of the things you have to remember, and that may trip you up, is that data actually also gets cached. So let's have a look. If you look in the home directory and we look in the cache directory, now there is a DVC directory normally, except that there isn't. Interesting. Sorry, it's .dvc and then cache. Okay, wrong directory. Okay. There is no cache directory yet. Okay, I'm surprised because there ought to be one, but there isn't. Okay. Likely it will appear later on. I can't quite see why it's not there yet. Okay. See whether there's something hidden? No. Okay.
May it be that the .dvc directory is being created inside the My project instead of your home?
There is a .dvc directory here. What did I put on?
And there you have the
Yeah,
cache.
you are right. Yeah, you're perfectly right.
Yeah.
Indeed. It's indeed here. There is a global .dvc directory, but that indeed does not contain the cache. The cache is here. Yeah, thanks. So basically, as you can see, this is the same thing. So it has the exact same structure as before. So basically, that means that files get cached. They are in your directory. So that also means that they count towards your quota. So that's something that you have to keep in mind, the file system quota. Okay, so right. So modifying data. So basically, if you change data, that means that nothing is going to change for Git, because if I edit that data.csv file, Git is going to ignore that. Simple. But of course, for DVC, there will actually be changes. So what we can do, very similar to Git, is do DVC status. And in this particular case, everything is up to date. Of course, I didn't modify anything yet. Now let me modify the file. So I'm going to edit the data file. In practice, you'll probably not do that, but rather run something that produces data or similar. But okay, let me just modify something here. Let's make this a 9. Doesn't matter what it is, what the change is. Okay, so of course, git status tells me everything's clean. Of course, I have been ignoring that particular file, so any change I made goes undetected by Git as designed, as by design. Okay, so let's do DVC status now. And as you can see, it says, okay, there is a change. We have a modification in data CSV. Okay, so then we can add the changes. And as you can see, that's again very similar to Git. We just do DVC add. Okay. So basically, it has been added. Nice. And its status, of course, we have a change. The metadata has been changed. Okay. Let's have a look at the difference. So basically, sorry, git diff data tvc. No change. Okay. So git commit m update data file. Okay. So now everything is clean again. All right. So then, of course, this is version control. So the question is, how do we get the previous version of our data back? Because now, of course, we have a new version of our data. How do we get the previous one? So what we need now is the git commit ID, which is relevant. So let's have a look at git log. One line is a bit more convenient in order to look at this. So basically, what we want at the end of the day is, for instance, here, this commit, because that's prior to the update I did. So if I can, for instance, restore this one. Okay, so basically what I do is a checkout of that particular commit. Okay, then I now, of course, I do have my metadata again. That is the new metadata, but I still need the previous version of the data file. So I also need to do a DVC checkout. Okay. So the CSV file has changed. Let's have a look at it. And you see indeed it's back to this 6 here, which I changed into a 9. So this is indeed the old version of my data. Okay, so basically you have to be a bit careful here because this will revert everything. So suppose that quite a number of things were changed in other commits after the one I'm checking out, then of course I would be in trouble because that's typically not what I want, because I might have fixed bugs in scripts that did whatever, that did my experiments. And then of course I would also restore those. I would also check out those. That's of course not what you want. So this works, but yeah, be careful. Another thing that can go wrong is that you forget to do a DVC checkout. Forgetting to do a DVC checkout basically means you continue to work with the version of the data you're not expecting. So yeah, that is not very productive. So you can go back to the current version just by git switch. Okay, and then of course I'm back to master, and of course I'd have to get my EVC data back. So basically EVC checkout. Okay, let's have a look. And indeed we've got 9 here rather than 6. So I'm back in the situation which I was before I looked at the previous version of my data. Okay, so as I mentioned, it's pretty tricky because obviously if you check out just the commit as is, all changes made in between are also going to get lost. Let me perhaps illustrate what I mean by that, because it's important that you realize what's going on here. Okay, let's add a very brilliant Python script. Okay, so I've added that under version control. Let's have a look at the log one line. And now, as you can see, the Python script itself is under version control. So let me go back. Let me do the exact same thing as before. So I'm going to git checkout to this commit. Okay. Now, of course, my Python script is gone. And that's most likely not what I want. So in this case, of course, the Python script just vanished. What would happen if it existed already prior to this commit was that it would be reverted to the state it was in at the moment of this particular commit which I checked out. And that is, of course, not what you want, because you reintroduce the bugs or the lack of features or whatever that you did meanwhile. So let's switch back again. Okay, let's not tempt fate. I'm going to check out. Okay. I don't think I need to do that, but just to do the things in the proper order. Not to have any surprises. Let me git switch again, and let me DVC checkout. And now, of course, my Python script is back here, and my data is again in the state it was in, so with the 9 rather than the 6. Okay. All right, so basically that's not what we want. So what we can do is simply check out, well, to simplify our life a little bit, we can simply look for commit messages that pertain only to the metadata file we are interested in. So basically to the data which which interests us. So one line, and then data. Okay, so there's only, oops, let's try insert the extra E here. Okay, so basically, as you can see, there are 2 relevant commits. This is the update, and that is the one which we had before. So basically, this makes it a lot easier if your commit messages are not that clean. Then basically, at least you can easily see which ones pertain to this particular data set. Okay. And then, of course, what you can do is create, for instance, a new branch for that experiment which you want to do, or that inspection of the data, or going back to the previous version, and then also restore only the data file. So let's do that. So I'm going to create a branch first. Let's call it experiment. It doesn't matter much. Experiment. Okay. All right. So I am already in a new branch now. So basically now I can do a git restore. Source would be this guy here. Okay. And what else do I need to do? Yeah, I need to specify the I want. So data DVC. Okay, that should be dash dash source. Okay, so I've got my old metadata back. So DVC checkout. And there we go. Let's have a look at the data file. I should have a 6 rather than a 9, which indeed is the case. There it is. There's my 6. Okay. However, the hello.py script is still there. So basically, this is the way to retain anything you want, all your recent changes to scripts, to whatever, and only get the data files, the old version of the data files back, or a specific version of the data files back. Okay. Let's git switch back to master. Okay. And DVC checkout. Okay, so this is one of the things that really can trip you up, forgetting to do this DVC checkout, because you live in the illusion that you have the correct version of your data, but the problem is that metadata and the actual data are not in sync. So now I should have the version with the 9, so let's verify that that is indeed the case. And oh, wait, where am I? Git branch. I am in master. Okay. Hmm. You. Something didn't happen as expected. Okay, let's check this guy out. Okay, let's see checkout. Okay. And now indeed, I have the version of the data I want. I don't know how that thing got changed. Probably I forgot something at some point, which is of course always the big danger if you are doing things interactively. Okay. All right. Yeah, so basically I switched back. I can delete the branch if I want, or I can leave it, whatever suits me best. But again, don't forget to do the DVC checkout, because otherwise you will be working with inconsistent data. Okay, so for an arbitrary GitHub repository, you can list the data which is in that repository. So that's nice in order to reuse data that is in different repositories. Actually, you typically want to add this -t flag in order to recursively list files. Otherwise, you just get top level. That's not so particularly interesting. One of the things that you need to realize that goes on is that actually under the hood, DVC is going to do a clone of the repository you specify, and it's going to search in that repository. So yeah, this may take a while if this is a large repository, because you need to do this clone, which may or may not be trivial. And then, of course, you can import data, a data set from Git repository, just using DVC import. You specify the repository and you specify the data file which you actually want to have. In this case, it would be a directory of some pre-processed data. Of course, that means something, and that something is that you need access to the remote for that particular data. So basically, if this were a local directory and I don't have read access to that directory, I can't retrieve the data. If it is an SSH or an SFTP remote, then again, I need credentials in order to access that data, because otherwise that is, of course, not going to work. So you can copy files as well, not only directories, but also files. Okay. Maybe this might be a good point for a shortish break, because we start on a somewhat different topic. This was a bit about version control of your data, which is very similar to Git, in fact. And that was the original purpose of DVC. How I got to know it, I don't know, 5 years ago, 10 years ago, I don't quite remember when I came across DVC. But since then, quite a bit of work has been done. And one of the things that has been added is the concept of data pipelines. And of course, data pipelines are quite convenient, because it means that if you have input data and you want to process that, typically that process consists of several steps. It might be pre-processing, it might be, for instance, dealing with missing values, it might be other types of pre-processing, then, for instance, some machine learning, post-processing of results, etc., etc. So again, in order to make this reproducible, you can of course work with shell scripts, but this is typically perhaps a bit brittle. And that's why there are many pipeline systems out there. In bioinformatics, I already mentioned SnakeMake and Nextflow as pretty popular ones, but DVC also adds its own. So the terminology differs a little bit across different pipeline systems. So in case of DVC, pipelines are built from stages. And basically a stage has dependencies. It has optionally parameters. It optionally also collects metrics. It definitely has one or more output, and potentially there is an action. There is an action associated to that. And this is rather nice. In fact, DVC doesn't care whether your action is Python or Bash or whatever. It doesn't matter, as long as it is some kind of script. So in that respect, it is sort of similar, but not quite, to, for instance, the Nextflow approach. Okay. So what is it mathematically? A pipeline is always a directed acyclic graph. So basically, each node in the graph is a stage. Each edge in the graph is determined by dependencies and by outputs. And that's essentially what a pipeline is. So it boils down to no loops. You cannot have something that loops, because that would not be a DAG, hence it would not be a pipeline. And that's a limitation that actually most pipeline systems share, because otherwise you can't guarantee termination, and that is an unpleasant property. Okay, so stages are cached, which means if the data for a certain stage has not changed, that stage is not going to be re-executed. So that's rather nice. It means that you can re-execute the pipeline, and that only those stages that need to be rerun will be rerun. So in that respect, it's similar to build systems like make or CMake, which will also only execute those build steps which are required by changes. Okay, so as you can guess, this is not something I'm going to type. Let's go through it step by step. Adding a stage is, yeah, quite a command. but you will recognize all the ingredients which I mentioned on the previous slide. So the command is dvc stage add, and you give your stage a name. These names should be unique and of course descriptive for what this particular stage is supposed to do. So in this case, it's about splitting data. So most likely we are going to split our data set into training and test data or something similar. So the first thing we need to do is to specify dependencies. So basically, we have a data dependency on our data CSV file. Okay, but there is another dependency which perhaps is not so obvious, and that is a dependency on the scripts which will be used in order to deal with that data. Now, in this case, that is the obvious script split data.py, but that contains a dependency. It imports a module, utils.py. So, in fact, all of these artifacts, all of these Python scripts / modules are in fact dependencies for this particular stage. So this stage will be triggered, will be executed when the data file changes, but also when any of these scripts change. So that's quite important. Then we have parameters. So we have a test size, basically. So that is the part which will be set aside for testing in this split data script, and also a random state. So that random state, of course, is intended to be reproducible, so that the split will be done deterministically when this stage is re-executed later on. And then there are a number of outputs. In this case, there are two. Yeah, obviously, a file with training data and a file with test data. Okay, so these are the things which were specified. So if we compare with the previous slide, let me go back for a second. You see we have dependencies, we have parameters, we have outputs, and we have an action. The thing which we don't have here is a metric. We will see an example of that later. But basically, this is going to be executed. And of course, the action is the call to the Python script, which is here. So basically, it's going to execute split data with a number of command line options, which are specified in that split data script. Okay, notice something that might be a little bit bizarre. You see params YAML there. Okay, so I didn't create that. That is going to be created automatically. So that is going to be part of DVC's magic. Then, of course, as soon as we've done this definition, we've added that stage, then of course we have to do a commit in order to ensure that that stage of the pipeline is in our GitHub repository. Okay. Okay. So parameters are by default in params.yaml, and this would be an example here. So basically, split data would have a test size and would have a random state. So this I can create and I can use in order to execute my pipeline. So there is another script going to run train model, and that has certain parameters as well, a penalty, C, whatever that is, and a solver, whatever. So basically, that's the idea. This can be either YAML or JSON. So basically, you can choose which format you prefer. I think this example is YAML, if I'm not mistaken. Yeah, indeed. So basically, you can have a params YAML file, and of course it's stage specific. Okay, so how do you use it in scripts? Well, basically, the easiest thing is in Python to just use the YAML library, and then you just open the file and you get the parameters out of that file. That's all there is to it, essentially. And of course, the file was passed. The file name was passed as a command line argument. Okay, and then you simply use the parameters as, for instance, the split data random state here in order to set the random state for the split. Okay. Yeah, that's reproducibility. Let's not go there. You're all aware of that. And this is one stage. So then we can add a second stage, and that is going to be a training preprocessor, according to the name. So it depends, of course, on the training data set which was generated, and it also depends on Python scripts. And it's going to produce a pickle file with the preprocessor data. And that's the idea. So basically, here, as you can see, we call again a Python script with some command line arguments. This guy has no parameters. So yeah, that may happen. And again, of course, don't forget to commit in order to make sure that this is in your GitHub repository. Okay. If you want to modify an existing stage, that's very easy. You just do dvc add force, and that should actually be dvc stage add force. The stage is missing here. So basically, you can also dvc remove and so on. So basically, that is quite straightforward. Now, the one thing which was missing was the metrics. And of course, in the pre-processing stage, typically you don't have metrics. But of course, if we are talking, for instance, training, then of course things get a little more interesting. So this is going to use a data file, preprocessed data, train.csv. It has dependencies on a pickle file that contains the model, and also on some Python files as usual. And then the metrics are in a subdirectory metrics, train YAML. And then we execute this particular script. And as you can see, we have an output here, and that is these metrics. So basically, this signals to the DVC pipeline system that this will produce not only output, which actually it doesn't in this case, but just metrics. So it's just going to measure something. And we'll see later why that is important. Okay, so you can visualize a pipeline simply using DVC stage list. And then you get something like this if you use DVC DAG. So that is going you see that this pipeline here, which I defined, it's actually going to give you all these steps. So basically split data depends on data CSV, etc. So here we have training preprocessor and so on. So you get this graphical representation of this DAG. You can have that either in terms of the stage or in terms stages of or in terms of the data files. So basically, if you have DVC DAGs out, you actually see the dependencies between the the data files one by one. Okay, so this can be rendered using dot. So if you have Graphis, then basically that can be done easily. Okay, so I can most likely show you. Let me leave this and let me go to the original, to the directory. Because if you want to reproduce that, of course, typing all these commands is a bit tedious. So if everything's well, I have a script here in order to reproduce the whole thing. Yeah, there is a setup script here. And that's just a shell script that is going to create this whole thing. Normally. Okay, let me have a look at the README file because this apparently does something else. Environment.yaml, blah, blah, blah. Generate data, put data. There is an init repository. That was the one I was looking for, and define workflow. So the define workflow was actually the one I was looking for. And that basically is a shell script that is going to, as you see, create this pipeline step by step. Because again, if you have to do that by hand, then of course, if you want to experiment with it, that is not going to be that easy. So in this repository, you can create a new repository with these files here. And then you can recreate that pipeline and execute it if you want. Okay. So yeah, that's nice. We defined it, we looked at it. So how do you actually run it? And basically, you can do that using repro. And if you just want to see, okay, what's going to be done without executing them, you can just use dry in order to check. And then, of course, if you just use DVC repro, it's actually going to execute the pipeline, but it will only execute the stages which are required. So if the dependencies didn't change with respect to a cached run, so to a previous run, then that stage is not executed. Okay. If you do want to run all stages, regardless of whether they had changed dependencies or not, you can simply use the dash force, which will just run everything. Okay, so that is going to produce a file dvc log, and that is one that should go under version control. And again, since we had auto stage switched on, this is going to be staged after the run, but you still have, of course, to commit it if you want to be under version control, and of course that should be the case. Okay, so essentially you can check the state of a pipeline as well, and then you see that indeed here a number of things have changed. So basically for split data, this guy has changed, and yeah, so that would be the case. Okay, so we defined metrics for certain steps. So the question is, of course, what do we do with them? And basically, DVC allows you to actually see these metrics, to collect them. So if you do DVC metrics show, you actually get the, in this case, the metrics for training and the metrics for testing. And you can compare, for instance, the accuracy or the F1 score, in this particular case, the precision, and so on. So basically, all of these are just stored in these train.yaml files and test.yaml files, which are just files part of your GitHub repository. Okay, so that would be for the most recent run. If you want to see differences on metrics, then you can compare, for instance, with the last commit by using DVC metrics diff. And then you see basically that you have several versions here. So basically these are the accuracies for the head, so that's the most recent commit, and the current run, so basically a run that you did but that was not committed yet, and you also get the changes for each of these parameters. So this would be the test accuracy, the F1 score for the test, the precision for the test, etc. And here you have the same for the training parameters. And you might notice that for test 1 is missing. Let me see, accuracy. So basically the recall is missing for the test. It's not that I forgot to copy it, it's just the change is 0. So this really shows differences. If some metric didn't change from one run to another, it's just not going to show up, which may or may not be confusing, but yeah, it's something you need to know. Okay, you can also compare arbitrary runs, and then of course we use commit um, um, commit hashes in order to change. So these were 2 runs. Or represented the commit after 2 runs. And as you can see, you get something quite similar. This would be one run, this would be the other run. These are the differences. If you want to see all metrics regardless of whether they changed or not, you can simply add -- all, and then you also get the 0 differences. Okay. So that was the whole game with metrics, which is quite interesting because it allows you to very easily compare the performance of, for instance, neural networks generated in different runs with either different parameters or different data sets or whatever you changed between those runs. And you can do a similar thing for the parameters, because also those were specified in the DVC stages, and you can also compare those. So for instance here, we compare the parameter settings between the most recent commit and the current version. And as you can see, the C for the training model was increased from 1.0 in the last commit to 1.5 in the current run. Again, you can compare arbitrary commits as usual. So here you see, for instance, that it was changed from 0.5 to 1.0. And again, -- all to get everything, because what did not change here, for instance, was the state and any pre-processing parameter settings like the test rate, the test fraction, and so on. That was not changed. Okay, so great. This works very nicely for Python. For R, it's also works, of course. There is nothing R specific here, so basically it would simply work. So in case you are using R, this is not entirely unlikely. In that case, the only thing which you need to know, of course, is how to read YAML files in R. And again, it's just loading a library and getting the configuration. So it looks quite similar to whatever you do in Python, only of course you get this list object, which you have to use the dollar operator in order to get the subkeys in this list object. Yeah, it's a dictionary, but R tends to call this a list for whatever reason. Okay, so this is nice. Now we have pipelines, and we can actually execute those pipelines time and time again with different parameters, with different, and they will produce different metrics. We can compare those, etc., etc. So this is already rather nice, but DVC actually goes a step further, and that is experiment management. So basically, in experiment management, you actually are going to modify the Python scripts that are part of your experiment, and that is using the DVC Live Python module, which comes with DVC. Okay, so obviously, if you want to do this, then of course the DVC has to be in your Python environment, because now you're going to import DVC Live, and that of course means that it needs to be in your environment. So the pipx thing is just for the executable, for running DVC commands on the command line. If you want to incorporate this into your Python scripts, of course, it needs to be part of your environment. Okay, so the purpose it serves is logging. So logging an experiment means storing the parameter values, the time step, for instance, metric values at that time step, images, plots, artifacts, essentially whatever you like. And then it can be used for report generation, and also to compare experiments. The nice thing is you can share that either just via GitHub or via that commercial part of DVC, which I already mentioned, DVC Studio. But again, you don't need DVC Studio. You can just share via GitHub. Okay, so basically, how does it work? This is just a small fragment of Python code. So it's just representative of something you would do. So you set a parameter, which is very unimaginatively called params. You create some system based on that parameter. Then you do a number of time steps. In each time step, you do something to that system, and you compute some metrics based on that system. And then you print the result to the screen. And at the end of the day, you save the system. This is, of course, all pseudocode, but you can imagine what this would look like if this were, for instance, a PyTorch training experiment. Okay, so what does DVC add to the mix? First, you import DVC Live, so that's just a Python module, and then you create a context. So with DVC Live, you say which format your report is going to be. In this case, it's HTML. If memory serves, you can also choose Markdown. There are a few other possibilities. So basically, that gives you a context, a live context, which you can use to do logging and to store metrics and so on. Okay. The nice thing is this is a context manager. So basically, that means if something goes wrong, then of course the context manager is going to try to take care that log files are saved, etc., etc. So basically, that you have the least dangling bits as possible if this thing crashes. Okay, so for instance, to log a parameter, very straightforward, live.logParameter, the parameter gets its value. Of course, don't do this at home. I mean, give parameters meaningful names, because this is a bit silly, but it's just to show where this is going. And then, of course, very similar for metrics. We have live log metrics and a metric, and that is again the name of the metric and the value of the metric. Okay. So basically, you have control over the steps. So you would have to call live next step in order to advance the logging system to the next time step. What you can also do, let's minimize this a bit. Okay, let's move that to somewhere a bit more innocent. So basically you can also log whatever artifacts you want. So in this particular case, what I would do is I'd log the model as it is now. So basically it's saved to a Python pickle file, and I can specify the type of this, and in this case that would be a model. Okay, so pretty straightforward. We can add logging for parameters, we can add logging for metrics, and we can also log arbitrary artifacts. That can be plots, that can be models, that can be whatever you like. Okay, so how does this work? Well, basically, you can run an experiment and that's just running your Python script as usual. So that will create quite a bit of stuff. It will create a DVC YAML file, and that is going just to contain locations of parameters, metrics, plots, etc., etc. And also it will create a DVC live directory. So that is going to contain a metrics file, a parameters YAML file, etc., and also the plots directory, and also the report. Okay, so essentially, plots are created on the fly. So basically, the raw data is also in the plots directory. Okay, what is going to do, how this is going to happen, in the sense that how is this going to be shared via GitHub? How do I know what all of this was? Well, basically, what DVC is using under the hood are in fact refs, Git refs, which represent these experiments. So that's how Git deals with these experiments and how you can share them using GitHub. You don't have to worry about this. You don't have to even know this. But I was just very curious because I didn't see anything change in the repository, and still stuff would happen. Just a second. Okay, this is not going to happen. All right. Sorry. Okay, so basically, this is a quite interesting approach and something I learned about Git that I wasn't aware of stuff that you could fiddle with under the hood. Anyway, what does such a report look like? Well, it's an HTML report. You can look at it in any browser, of course. And then you see, for instance, and maybe I should tell you what this experiment is, because this is a bit weird. You see magnetization and you see here a step. So just to make the point very clearly that this is actually nothing to do necessarily with machine learning. I actually implemented this for quite a different type of experiment, something that you do in statistical physics. So basically it represents an Ising model, which is essentially something you can use to model magnetism, ferromagnetism, anti-ferromagnetism. Yeah, I think so. At any rate, ferromagnetism. And basically, this is the magnetization which evolves over time. So here we have the energy. So the system also has a certain energy, and as you can see, that drops and it starts fluctuating basically because we are at a finite temperature, and that temperature should be here somewhere normally, but I don't quite see it. Rows. There should be a temperature here. I don't know where it is. Okay, whatever. So basically, again, if you would like to reproduce that, no problem. You can. That would be in a different directory, and that would be experiment management. It's most likely, no, it's not, I think. I don't think. Yeah, hard to read. Let's have a look at the experiment file. Normally, that would be the one. Parse arguments. Let's see what we have. Okay, so this is just an abstract, some abstract experiment, but basically that's the one for this example on the slides. Now I'm wondering where the easing thing is. It should be here as well. Question is where. Let's cheat and try to find it this way. Okay, likely it's this guy here. Yeah, here it is, indeed. So basically in experiment management, you will find the source code in order to run this. As usual, there is also a setup script to prepare things and so on. So if you want to run it and look at that report, then of course you can do that. Okay. So basically here we have the parameters. That's the top row, and these are the metrics. And this is of course at step 500, so basically at the end of the simulation, but you see the evolution of these metrics just here in the plots. As you can see, it's somewhere around 0.5 here, and the temperature, sorry, the energy is negative at -1.2. Okay. Basically, these files are, these plots rather, are based on the tab-separated value files which live in that directory I mentioned, and they're actually generated on the fly. So that is rather nice. They are also interactive. You see these sliders here. So basically, you can smooth that plot a little bit if you want. Yeah, that may or may not make sense depending on how you want to analyze your data. Okay. The nice thing is that you can just use -- open in order to get that if you're on a Windows system with WSL2, which is rather nice. Okay. So you can list experiments. You can list all experiments. So not only at head, but also at different commits. And you can save a workspace as an experiment. So basically, the workspace, that's of course your working environment at this point in time. You can simply save that and give it a name. Okay, you can also rename experiments. So note, it's always dvc exp and then a subcommand. And you can remove experiments and so on. So you can view them also, let's say, in textual form. So for instance here, I'm using dvc exp show. I only want changed values, and I want them in Markdown. So basically something that is a bit easier on the eyes if you plot it, well, if you show that in a terminal. A small trick here, the problem is that DVC-Exp show is going to produce very wide output. So something that is typically not going to fit in your in the width of your terminal. And it's also going to use a pager. So what I'm doing here is I'm setting the -S option for less, which is the pager that it uses by default for me. And this basically says that it doesn't do any line wrapping. So basically I can scroll horizontally if I want to see all the columns, but it's not going to do any wrapping. Otherwise, this is just illegible and you can't interpret the data. So as you can see, in the workspace, we do have a magnetization. So that's the most recent experiment of 0.9734. And basically, in the main, that would be a different value, same for the energy and so on. And you see that this parameter, which is a system parameter, indeed changes between those two values. And that, of course, is a reason for a different magnetization in this case. Okay. This is the last trick, which I already mentioned. What you can also do is create JSON output or CSV with no pager, and then you can use, for instance, CSV kit in order to select certain columns or to format those columns in a more user-friendly way. So you've got a CSV cut, which allows you to select columns in a CSV file, and CVS look changes how this is rendered in the terminal. So I can recommend this. It's general tools which can be quite useful. Okay, so you can also do plots. So for instance, I have an experiment called high temperature, and I can show the plots here. And then you see that indeed you get the difference between, on the one hand, no, this is both for the workspace, sorry. The revision is both the workspace. This is the energy, and that's the magnetization. So again, this is going to be an HTML file, which I can simply manipulate using this slider here, for instance, to get a different smoothing for this particular plot. Okay. Again, those are created on the fly based on these tab-separated value files. Again, adding -- open is going to immediately open those things, at least if you do that locally. That, of course, doesn't work if you do that on an HPC system. Okay, so you can compare experiments using DVC-X-diff, and then you specify two experiments. So I renamed particular experiments to high temperature and low temperature. And if I do a diff, you see that these are the metrics for the energy, for the high temperature, and the low temperature, magnetization, and you see also the changes. So basically, that's for the metrics, and also for the parameters, you see that the temperature indeed changed from 2 for the high temperature to, okay, that's weird, to 5 for low temperature. Okay, this is very weird. Okay, probably I mixed them up, and one should be high, the other should be low. Okay, never mind. You see where this is going. Obviously, I did something stupid here. Okay, weird. Never mind. So basically, you can also get that as plots. So essentially, this is what you get here. You get a plot with the two curves on the same plot. So you get all this automatically. You don't have to do anything specifically to get this. It's just automatic because everything is recorded. So I mentioned that you can actually share experiments, and this you do with DVC X push. And of course, you have to tell it where to push. So basically, that would be the origin. And now, of course, origin refers to your remote in your GitHub repository, which is typically GitHub. And you can, of course, pull experiments from GitHub and analyze results of, for instance, your colleagues or other coworkers. Okay. Yeah, it's a little bit weird that you really have to specify a remote, because normally Git has the convention that if you don't specify a remote, it's going to be origin. Yeah, here that's not the case. I don't know why, but anyway. Again, don't forget to DVC pull and push if you want to get your data. And of course, not only git push, git pull, also do DVC push and pull, because otherwise your data for your experiments is not going to be updated in the remote storage and hence not available to your coworkers. So that's something that you really have to remember. It's not just Git anymore, it's also DVC. Okay, so in case you're interested in how to do this in R, it's actually very easy. The only thing you need to do is to load the library Reticulate, which allows you to run Python in R scripts. You import DVC live, so it's very similar actually. The thing that changes, of course, is that R doesn't have the concept of a context manager, so you get a live object. You do the same things, so you log parameters, you log metrics, you do next step, etc. You log where is it? You potentially log an artifact, but what you definitely should not forget is to do live end, because that's basically making sure that everything is saved properly and that all data is pushed to the external sources. So don't forget this. You don't have to do this in Python because the context managing is doing it for you, but in R, no context manager, so you have to do it yourself. So that's quite important, otherwise your data might be corrupt. Okay. This might be, again, a good time for a break.
All right. May I ask a question? Maybe
Obviously.
just repeat for the
We did have DVC data control. That was its original goal. It does that quite well, and it's quite useful. We have the concept of pipelines in DVC, which are also quite useful. And we have the concept of experiments in DVC. And now we can combine the whole lot. We can have experiment management and pipelines. So that's basically combining the two previous sections. So basically, an experiment is going to be a stage. That's the idea. Train your model, for instance, after you've pre-processed your data, etc., etc. So an experiment is essentially a stage, and an experiment is going to use DVC Live in order to record, let's say, runtime metrics, for instance, the accuracy, the loss, etc., etc., of some machine learning training process. And this is done using DVC Live. And basically, you keep track of a number of things. the pipeline is going to keep track of dependencies of relevant parameters at the end of the basically the parameters which are used for a particular stage. You can also record those using DVC Live, but still they are also part of the pipeline, similar for metrics and for outputs. So that's essentially the idea. So to have experiments in pipelines, so it's just like adding a stage, it's the same thing. And then, of course, the action of this pipeline, the action of this stage contains calls to DVC Live in order to do experiment management. And parameters are still read from the params.yaml file, so basically from the one you specify in the stage parameters setting. So those form the input, which of course is recorded as part of your experiment. So you can run an experiment just with DVC run, and you can run with particular parameter values as well. So then you just use the -- set param and a different parameter setting. Okay, so that is going to modify params.yaml. So again, remember this means that you would have to commit this, stage and commit it using Git for version control. For instance, you can prepare a workspace for a particular experiment by just doing DVC apply and the name of that experiment. Okay, now things get interesting because one of the things that, of course, that you typically want to do is you want to run your pipeline, but you want to do hyperparameter optimization. So basically, that means that typically the pre-processing may or may not be governed by a hyperparameter. Probably not, but might be. But certainly, for instance, training would be subject to change if you have different hyperparameters. And that is something that can be done. You can do parameter sweeps using experiments. So basically, experiments can be queued into, so now we are not talking a batch queue such as Slurm or something. So this is something internal. You can also queue entire parameter sweeps. So basically, in this case, I want to run an experiment and it's going to be queued. And the user parameters are, in this case, these three here. So there will be run an experiment where A has the value 3, where A has the value 4, and A has the value 5. Okay, so this was just queuing. And you can run now all these experiments one by one after the other, just with run all, -- run all. So everything that's queued is going to be executed. You can check the status of a queue. Basically, once it's running, you see that these here are queued. These three were finished. So apparently at this point in time, nothing was running. They were just either done or queued. Okay, you can show the logs. So basically, this dopey thing is essentially the name of one of these experiments. So they're not, I didn't invent them, they're just auto-generated out of 2 words, which are then combined to form something that's hopefully unique. And you can look at the log files of that particular experiment. Of course, in the log files, things like errors will pop up and you will want to see this. You can remove experiments that are either queued or completed just by queue remove with the name of the experiment. Okay, so besides running tasks sequentially, you can also run them in parallel. So basically, you can define a number of workers, which then, in this case, would run 2 experiments concurrently in order to get more work done in the same amount of time. Of course, yeah, does this map well onto an HPC cluster? That's a bit doubtful, because basically what you have here is a job that would run 2 experiments simultaneously on a compute node. So you would have to be very careful with, for instance, GPU usage. Which experiment is going to use which GPU? It's not obvious, because if you ask for 2 workers, you will have 2 GPUs. Which one is going to be to use which one? I mean, this is going to be a bit tricky. So basically, this might not be your best approach on an HPC system. It can be useful on a local system, but on an HPC system, I'm not very enthusiastic about this. You can specify as many jobs as you want, but of course, if you oversubscribe, you are going to get a pretty bad performance hit. That's pretty obvious. When the workers have been started, you can stop them. That's easy. And you can also kill all of them, just adding the dash kill flag. You can also kill a specific task. So if you're not convinced that a certain experiment is going the right way, you can just individually kill it as well. Okay, so this is possible. This queuing thing, is this useful? I don't know. Again, on an HPC system, I'm not really that convinced. Okay, so basically, a few takeaways. The advantage of Git and DVC is that it's standalone and that it's pretty lightweight. Git is installed anyway. DVC is very easy to install. You're familiar with GitHub. Essentially, that's all you need. And it does promote, if used correctly, reproducibility for experiments, for workflows, and so on. And of course, it also allows you to share data, to share experiments, and to share models quite easily, just using GitHub and a remote storage, whatever that is. So basically, that helps. The major hurdle here is discipline, or more precise, the lack thereof, because of course you need to be very careful to properly use version control, in the sense that you always have to remember to commit, you always have to remember to DVC check out, etc., because otherwise you may end up running an experiment on the wrong data because you forgot a DVC checkout, or you might accidentally not record certain parameters because you forgot to do a git commit. So basically, you really need quite a bit of discipline using both version control and DVC, so both Git and DVC. And you have to use them properly in tandem, because otherwise, again, you will create inconsistencies. So this is documentation, and that is, if you like, you can play around a little bit with these experiments. There are some specific directories. Usually they have, so this would be a combination of pipeline and experiment, for instance. So basically, normally, there is no setup here. Okay. Normally I do have a setup, but not for this one. So that means that, yeah, you would have to do the work by hand, I'm afraid. Let's have a look at the README, because I'm very surprised that there is no setup script. It's actually here. Okay. So basically, it's in the README how to do that. So this is, yeah, a very short pipeline in the sense that it's only one stage. So that's not particularly exciting. But of course, you can easily extend that by adding some data pre-processing or some post-processing and so on. So I would invite you to play with this and to get a little bit familiar with how that works. What else is here? There's another directory. Oh yeah, that's just how to deal with YAML in R. So that's not particularly exciting. Okay. So now it frankly depends a little bit on what you would like, because there are a couple of options. Right. So this is not in the CASTIEL repository. I'll add it because I wasn't really planning on doing this, but okay, that's the one. All right, so as a matter of fact, you do have this presentation in the sense that this is actually the fine-tuning part and the quantization part yesterday is part of this presentation. And when I originally put this under version control in the CASTIEL repository, this was this presentation, so the complete presentation. So in fact, you can already get it from there, but I'll upload it properly later on. Okay, so we know this, let's not go there. This slide you might recognize because I showed you this one yesterday and said, ah, damn, I forgot to update the table of contents. Okay, so this we saw yesterday, not relevant. Right. Okay, why would you like to deploy large language models locally? Because, okay, I mean, why bother? There is ChatGPT, which you can query via web interface. There are various others. So why bother? Well, of course, one of the reasons is that your data might be private. It might either be intellectual property which you don't want to leak, or it might be sensitive to GDPR because it contains some privacy issues. So that's one reason. And of course, if you look at the end user license agreement of OpenAI, they say that they will not do anything with your data that you upload, etc., etc. Okay, you can believe them. That's nice, but your DPO is not going to believe you. So your data protection officer is going to be hopping mad if you upload private data to OpenAI or similar, regardless of end user license agreements. No one believes that. Okay, so that of course is already an issue. And then another issue is of course latency, in the sense that, well, we're in Europe. There is a big difference between the response time of a large language model in the morning, well, when everyone in the States is sleeping, and in the afternoon when they wake up and ask for summaries of their emails. So basically, latency is an issue, not only with respect that it may vary wildly, but also, of course, just if you do an API call, that's nice, but you have no guarantee on the latency involved, because there is quite a bit of network between that, and basically you don't know. Then, of course, there is also the potential problem that your vanilla large language model may be too generic, so that you want to do something. The something might be fine-tuning, which we discussed yesterday. The something might be RAG, which will be discussed tomorrow. So the various things you can do, but they involve at least some local manipulation. Okay, so let's skip this. I'm assuming that you know what LLMs are. Yeah. We know. Okay, I should do this a professional way because otherwise we're still here tomorrow. Let me go to the next section. Okay. So basically, you can run large language models, well, sometimes maybe even on your own infrastructure. And of course, own infrastructure in our context is actually HPC systems. And of course, it depends on the number of things. It depends on the hardware. So how much CPU power do you have? Because you still need some. Also, very importantly, how much RAM do you have? And do you have a GPU? How many GPUs do you have? Which types are they? Etc. etc. And then, of course, it also depends on the training, on the task you want to do. Inference is easy, with air quotes, of course. But training, of course, is a totally different kettle of fish. You need way more memory in order to train than you need for inference. And of course, yeah, you can run those on HPC systems. So there are a number of ways to run LLMs locally. And one of them is Olama. The advantage is that it is very simple. It does quite a lot of stuff simply out of the box. And it has quite a number of good quality large language models that you can run on top of them. So, for instance, the Llama series of models, Mistral, Gamma, which is a Google model. So basically, there is quite a number of things you can run. Back in the days, I frankly didn't check whether that's still the case or not, but the problem was the install script, which you run in order to install Olama, really insisted to install the binaries in user local, which of course on an HPC system is not an option. So either you start modifying the install script, which may or may not be a good idea, or alternatively, you just run in a container. And that, of course, is something that is portable, so that is quite convenient to do. Okay, so maybe let me just do that. And I'm going to do this locally because I didn't install Olama on the HPC system. So I'll do this locally. Let's get out of the shell. I don't need it anymore. Let me start Tmax because I need multiple shells. And let's start with Olama serve. Basically, this starts the backend, and you need that in order to do anything at all with Olama. So I can now Olama list, and that gives me a list of the models I've got available. And you see that in my case, there are, I'm going to increase this a bit. Okay. This is just to keep an eye on what the server is doing. So basically, as you can see, I have access to quite a number of models, and you see that one of them doesn't have a size, and the other ones do. So basically, these are models which I downloaded and which I can run completely locally. The top one, as you can see, there is a suffix cloud here. So since a couple of months, well, 4 months likely, Olama actually allows you also with the same interface to get access to cloud-based models. So they, of course, don't run locally. They run somewhere, depending on, well, no, not somewhere. To be very precise, on the hardware Olama makes available. So the advantage of that, of course, is that you can run pretty large models in order to experiment. As you can see, this would be a 120 billion parameter model. Running that even on an HPC system is going to be, okay, a little bit challenging. Not very challenging, but a little bit. Of course, what you can run locally are very small models. So for instance, here is a 4 billion parameter model, a very small one, 270 million parameters, and so on. So basically, there are quite a number of models available. And I can simply run one of them by just saying Olama run, and then the name of the model, let's say, I don't know, Lama 3.2. Okay. Now, as you can see, lots of stuff happens in the upper part of my terminal. So basically, the model is being loaded and started to be ready for interaction. So this does take a while because, yeah, this is a fairly large model. Okay. Okay. All right. So, no, not yet. Thought it was done, but as long as this thing is spinning, I don't get a prompt. So this is now running on my local GPU, which is an RTX 3000 something. We can check. Don't remember. So basically, this is a GPU. You see that it gets some load. And the type is somewhere. Where is it? Here. A 3060. So a fairly old one by now, but it's still quite serviceable. As you can see, it has 6 gigabytes of RAM, if memory serves, and which I actually would recommend over Olama if the chips are really down. So now I can start querying this model. As you can see, I have a prompt, so I could ask some question. Let's make the settings. Slurm. I'm very curious what the answer will be. Okay. Okay, it's a bit fast, but I think that actually the answer is reasonable. Yeah, that's quite reasonable. Okay, and it even tells me the basics of a job script. So yeah, whatever. Okay, but as you can see, this works quite well. Response is pretty quick for a very modest hardware. So that's rather cute. One of the things, again, that you can be bitten with is that, of course, these models are stored somewhere. And okay, they're not that huge, but frankly, on my system, that is getting a problem. So basically, I don't store them in the default location. I prefer them on a different file system and very much away from my home directory. So that's something that you control with the Olama models environment variable, and that allows you to control where that goes. Okay, so basically, this I already showed you, listing installed models. What you can do also is get a model without immediately launching it. So if you run a model, it's not there yet, then first this pull is going to happen, or you can first pull and then run it. So in this case, this would get code llama in. You can get information about the model. So basically, let me split this again. So another info. No, show. So Lama 3.2. So that basically gives you information about this model. Fascinating things like the license, not so very interesting, but also all kinds of parameters here. So you can see the number of parameters, obviously the length of the context, embedding length, and also the quantization. So remember, this is the quantization level. I didn't discuss this in detail yesterday, but this essentially is a quantization level. Okay, so it can be used for completion and apparently it's also tools capable, whatever that means in this particular context. Okay, what else can we do? You can remove a model, which is a very good idea if you're short on disk space. Just Olama RM for remove and you're done. Okay, so again, this is running, not particularly exciting. You can run multiple models simultaneously. So the same server process can actually serve multiple models. I can try this. I'm not sure how much. Okay, let me first list it. I don't remember the name. Okay, so let's try this one. I'm going to run the 270 million. Okay. It still seems to try and do it. Never tried this before, so I'm quite curious whether it can cope with it or not. Let's try something here while we wait. Okay, let's challenge it a little bit. Okay, now of course I'm pushing things, so okay, I've got my prompt here. And I get the correct answer for 3 plus 5. That is very encouraging. Let's see here. Oh, it even does the right thing as well. Brilliant. Okay, so as you can see, I can run multiple models simultaneously. Of course, I especially I on purpose chose a very small model as the second one because yeah, this is really pushing the envelope on my system. Okay, so to get out of the prompt, you just type /by. Okay. Yeah, that was stupid. Let me maybe run it again. Okay, so let's go here. Let's split this as well. And now you see that indeed two models are running. You get the size, you get where they are. So they can be entirely on the GPU or CPU offloading may be used. So, well, okay, not CPU offloading, but basically layers can be distributed among GPU and CPU. So basically that is quite useful as well, that is at least an option. I can kill a model here. So basically, Banana stop, I think, if memory serves. Let me see whether that works. Oops. I have to remember that I'm Tmux. Okay. Okay, I don't know what I did, but something stupid. Mm, mhm. Oh. Let's put that into more parts. That's not so very good. So let's try to paste that? No. I don't know why it's Microsoft. So that was Villa 3. 279. Let's just lump it. Okay. And as you can see, normally this guy now should have stopped, but it hasn't, apparently. Okay. So yeah, that does not really work. You can't have it all. Okay. Is it really still working? Let's check. Okay. Ah, no, it's actually stopped. Okay, that's great. So that begs the question, what is happening here? So probably if I try a query here, nothing is going to happen anymore. Let's see. Okay, apparently it still is running. That's quite fascinating. It's back again. Okay, so apparently, as long as you have a client and you execute something, then it gets started again and it's still there. Okay, anyway, that was just satisfying my own curiosity. Let's quit this guy. Okay. All right. So that's quite easy. Of course, you're limited by mainly the available RAM, not necessarily on your GPU card, but on the system as a whole. So that is a limiting factor because it will offload to the CPU, to the RAM if necessary. What is also very nice is that if you have multiple GPUs, it's also going to use them and it's going to do a pretty good job automatically. So that's also a very nice feature. Okay. So basically, this is one possibility. So Olama is nice. It's easy to install. It's very easy to use. So that's definitely a selling point for a quick experiment. This is quite nice. On the other hand, I already mentioned for what I would call production, I'd not necessarily recommend it. I did experiment with VLLM. So the advantage of VLLM is that it gives you infinite control over how your model is deployed, in the sense that, for instance, it allows you to control the caching of the attention mechanism. So basically, there is, if you can do attention caching, that is very good for performance. And so basically, it allows you to set aside a portion of the memory in order to do this. It allows all kind of configurations. So that is an advantage. The drawback is that it took me 3 or 4 attempts in order to get a model running, because you have to fine-tune these parameters. If you don't fine-tune them, your model is just going to crash. If you have the wrong values, it's just going to crash. So basically, it's significantly more involved to get something to run properly. But it should run faster. It should give you much more control over what happens. That also means, of course, that you have to be familiar with the specific architecture of the LLM, that you have to know how big the tensors are that control the attention, etc., etc. So yeah, much less trivial than this Olama. Okay, yeah, we know. That's all not particularly interesting. A thing you can do with Olama, that's rather nice, is creating your own models. Okay, that sounds very, how shall I put it, exciting. Reality is a bit less exciting in the sense that what you can do is you have a model file that contains the base model you want to start from. You can control parameters. So most LLMs have a temperature as a parameter, which defines their, shall we say, creativity. The higher the temperature, the more creative it is. The lower the temperature, the more reproducible it is. So yeah, that's something that you can control. But you can also set a system prompt. And in this case, I set it to be an HPC help desk person, but with the personality of Marvin, which you may know from the Hitchhiker's Guide to the Universe, the paranoid robot who was permanently depressed. So basically, that is output generated by this particular LLM. I can't show you, I had to remove it because I had not enough memory, well, disk space left, but okay. So that's interesting to know that you can rather easily customize LLMs if you want to. Okay. Right, this is, yeah, okay. Yeah, so this is about racks. I'm not going there. But that's a subject for tomorrow.